And we'll start recording. Yes. So as a reminder, on this class portal, on the workshop portal, you'll find a wealth of material, and I'm continuously updating it. A few things to pay attention to: quizzes. When the quizzes are released, please do take those quizzes. They are an integral part of learning. Then we have the lab code, the zip files, uh, download those archives and use them or upload it to your cloud, Google Drive or wherever it is that you want to do. Uh, that is another thing to do. The third is the surveys. Do please take the surveys. Surveys is how I know whether you have understood something or not and what topics to repeat. Whatever people have not understood, I'll be happy to repeat in the weekend those specific topics and come to that. So for example, at this moment, the Tuesday's session is here. If you were to click on this, it will take you to the YouTube recording. Likewise, the quiz and the discussions are here. Today, I uploaded the week 2 lab and homework. So that's all I have for the administrative stuff. Now, I would like to start with a bit of good news. Most of you have heard Geeta Alluri. She was a participant with us last year, and she got first into Walmart Research Group, um, Walmart Labs as a senior scientist, and now she's gotten an offer from Amazon. And one of the things she mentioned, which I feel quite proud of, is that she said that the Amazon interview had a lot of theoretical questions, deep, in-depth questions, and because of what she did in the workshops, uh, she could do very well. So I suppose um, that is good for me. Something is working. And for you, it also means that try to review stuff. It will actually come in handy. The theory part also, not just the lab part. It isn't enough just to know how to code. It is important to know the foundations. Whenever you go and interview with some of the big guys, they'll always grill you on the foundations. So it is important to know the foundations. And so we are ready to start. Any questions, guys, before we start? Anybody has a thought?
Asif,
Yes.
the homework, the tar file that you're uploading, is it cumulative? Does it include last
Oh,
year?
yes, of course,
I
cumulative.
see that it creates the same folder set again.
Absolutely. It will always be cumulative.
Okay,
So
thanks.
that project will keep growing. And I will be, now I'll be giving this week some tangible things to do in coding. And so next week I'll release the solutions to those. Any other questions, guys? All right, guys, if you don't have any other questions, then I would like to share my writing board, and let's start here. Last week, on Monday, just to recap, we talked about the fact that neural networks are universal approximators. They can adapt to any function, any reasonable function, one would say, very effectively. And they approximate it well. It doesn't have to be exact, but they are good approximations to it. You can, in fact, do that with just a single layer in the neural network, one single hidden layer. That's a remarkable truth. Now, the things that improved in that theorem, there are versions of the theorem. One proved, the earliest version said, you need the logistic function. It said you need the sigmoid function. The work after that showed that it is not a property of the activation function, but it's a property of the network architecture itself. If you have a hidden layer, then your neural network will be able to approximate any function. And Lastly, then, we live in the world of deep neural networks. You'll see that we don't have one hidden layer. We have many hidden layers. In fact, we have nowadays a shocking amount of hidden layers sitting in neural networks. These neural network models are extremely large. So there is a version of the universal approximation theorem that says that it
Green
works
looks
for deep
black.
neural networks also, which is sort of the, people think of it as the transpose one. So you have a choice. Either you have one hidden layer which has a huge number of nodes, or you flatten it out and you have many, many layers with lesser number of nodes per layer. Right? It still works. So then the question comes, how does neural networks solve a problem? What are the core ideas behind solving? So towards that, I'll just today, I'll not focus too much on the theory. I'll give you guys the big ideas because we want to do the lab today. So this, just as a review, so go back to linear regression. If you remember, in linear regression, we had, let's say that you have points. Let's take some points. Are these points visible? So suppose you have points like this and a few, and you try to fit a line through this, right? Within some coordinate system. So this is X and this is Y. This is a recapitulation. Regression is, remember, in this particular case, you're going from R to R, right? So this is your line that you're searching for. Now, whether it's a line or whatever it is, one way to quantify how good your model is to look how well this line fits to the data. And the way you do that is you ask if at a given value of X, let's say I'll make the XY axis, at a given value of X, let's say this value, the reality was this. And what was the prediction? This was the prediction. So this is the Y, this is the Y hat for this particular value of X. Right? So the mistake that you made, the gap or the error for this point, let me call it Xi. So this is Yi and Yi hat. So you say that the error that you have, that is often written as a epsilon I, and it is also written as a Ri. So you can use whichever notation you like. It is equal to Yi, the true value, minus Yi hat. Right? So this is a recap, guys. I hope this is obvious that this is the amount of mistakes. This line, if it is the model, at this value of Xi, it will say this is the value of Y. So this is your Y hat. But the reality is this is the data, training data. And so you know the mistake. Now, how do we learn? When the machine learning learns, it learns by reducing error. We talked about the process of learning. Learning is reduction of error. Errors. Right? More formally, what you talk about is the loss function. Loss function, which contains the sum total of all errors, and you throw in a few extras, like you throw in things like regularization and so forth. And almost all of you have done those things with me in your prior labs, in your ML100 and 200, so you're familiar with it. So without further ado, I'll just mention that the loss function for regression, what is it? Would somebody like to say? It is made up of, it is essentially the sum of all these errors, epsilon i's, squared. Sum squared error. That is why people also say sum squared errors. So this is one. Now, what people do, and so depending upon the literature you're reading, what people do is sometimes they say, let's take the average over the number of points. So suppose the total number of data points are n, you take the average. Now you get a mean squared error. right? So whether you take the average or not doesn't matter, because after all, this is this particular thing, 1 over n is a constant. Given the data, it's a constant. So if you try to minimize the loss, you will end up focusing on this part. Now, what is this part made up of? This is a recap. This part is made up of yi minus yi hat squared, and that is equal to, so now the question, now comes the specific thing for regression. What is your model? Right? You may have some equation for the model, and that will determine what your gap is, some parametric model. So I'll just write this word, some parametric model. And I will sort of avoid the temptation of writing the equation for linear regression, because today we are going to get into deep neural networks, and the number of parameters are huge. So we don't want to fall into the trap that we are thinking linear regression when it is a bit more complicated. But this is not enough. While this particular is the sum squared term, there is more to it. There is a regularization term. Would somebody like to give a quick 10-second summary of what is regularization? Any volunteers?
It's how you dampen the effects that can cause
That's right, dampen the effect of
um, excessive variance.
excessive variance. That's right. So what happens is when you overfit to a model, your variance goes up. In other words, you start seeing a lot of undulations or bumps or oscillations in the function that you create. And so one way to tame it, one way to improve the situation is that you add a regularization term. For example, the L1 regularization adds a term. It basically dampens the weight. So suppose the weights are W, right? I will just write the weight vector, the set of weights as W. It will do it by saying there's a penalty term. If you make the weights too big, then your loss will increase. You need to keep your weight small enough. The L2 version of regularization, and I'll talk what this L1 and L2 are in case you have forgotten. I think when I look at this audience, all of you know, I can see almost everyone knows what L1 and L2 is. Could somebody tell me the more popular names for L1 and L2?
L1 is lasso.
Lasso.
One is lasso, other is ridge, and then there is a combination of both.
Yes, which is the
Elastic net.
excellent lasso, ridge, and elastic hybrid. It's a combination of L1 and L2. And so its effect is essentially that. Now, there's a bit of beautiful geometry associated with it, which has to do with Minkowski distance and so forth. We won't get into that today. So we will take this as a milestone result for today. Let's say that I'll just write it in bold here. This is one of our milestone terms. So now what do we do with the loss function? We try to reduce the loss. And the more we reduce the loss, the more our line or hypothesis surface. Now here it's a line in 2 dimensions, 3 dimensions, it would be a plane if it was a linear regression. But you can have a regression in which it is not necessarily a line. It's some curve or some surface. Last time we saw that the universal approximator property was fitting to all sorts of data, all sorts of functions. So each of these functions is a curve, and in higher dimensions, it's a hypersurface. So now, what are you trying to do? You're trying to, essentially, your goal is this. Goal is to, let me take a little blunt pencil. Goal is find that, is this visible, guys? It's too thin, perhaps. Find something is happening. Find the hypersurface the surface that is best fit or closest to the data set. So here we see that the white line is closest to the green points. Considering that the green points are sort of scattered, there are error terms here, noise here built in. So we can never have a perfect fit to all the points unless you have a very, very complex model, and which intuitively we know is wrong because that is overfitting. So this is our goal. This is what we try to do. Find the hypothesis surface that is best fit to the data set. And that goal is the same as finding, this goal is the same as mathematically, what it means is you find those parameters, argmin, the weights, let me just call it those weights. And so that is why these are called W star. Find those weights or the parameters of the model that will minimize the loss, the regression loss here. Are we together? And you think of the regression loss as built upon these parameters. Remember, we talked of the rheostat model last time. At the end of it, what can we control? Just move the slider of the rheostat back and forth. Data is given. We can't change the data. So when we build a model, either we can change our hypothesis, but if we have a hypothesis, let's say a linear hypothesis of a surface, then all we can do is tilt the surface, right? One way or the other. And that is the same as changing the parameters or the slopes of that hyperplane, isn't it? So that is it. So you say that W star, the optimal, and so you'll see me use this notation. Whenever you see star associated with parameters, by the way, just about a parameter, we used to, in the prior courses, use beta as parameters. But in the neural network world, it is much more common to use the word weights interchangeably with parameters. And W is much more used, little w, and then capital W for the matrix. And so the optimal value we will represent with a star. And this is our problem. We want to find that value of the parameter vector, of the weight vector, essentially, that minimizes the loss. The question then comes, how do we minimize it? And so we will go into that part right away now. So this is part one of the journey, right? So let me mention this. This is one part. You are trying to minimize the loss. So guys, this notation looks cryptic. I hope it is you're understanding it. You're saying that argmin means, suppose this is the input, this is the output, loss is the output. If you look at this equation, based on the values of the parameter, you'll get a certain loss value, right? Loss, which is a function of the parameters. So you can keep changing your hyperplanes or your surfaces, and for each of these, there would be a different loss value, loss amount. You are searching for that argument of weights, in other words, that hypersurface that minimizes the loss. That is all that this succinct notation says. It says argmin. Argmin here means W. So it says those values of the weights that minimize the loss function are the weights we are searching for. W star are the weights that minimize the loss. That's all that this statement says. Huh? It's a mathematical notation, and we'll use that. So now the question comes, that is fine. We know what our goal is, but how do we get to that goal? We still haven't found a way to get to the goal. Now, towards this, I will give you guys a review of what we have covered in the past, but this is for those, just in case you forgot. There is the process that we use is called gradient descent. And why it is called gradient descent, you will see in a moment. So you realize that your hypothesis leads to weights, each of them has weights, and it leads to a loss function. let's see what this loss function looks like in a moment in a higher dimension space. And on our website, we have a wonderful section. We have a section. There are people who have studied this loss surface, the loss function very deeply and created beautiful visualizations for it. We'll go into that, time permitting. Otherwise, we'll do it on Monday. Today is a lab section, so I will bring about just enough knowledge to get us there. So what is gradient descent? Imagine that you have a function, something like this. This is your x, this is your fx, y is some function of x. Are we together? Now, there is a concept of slope, just as a basic review of what a slope is. What is the slope of a function? What is the slope of x? Would somebody remember what is slope?
Like
Slope.
the derivative.
Incline. What is the incline or slope? At a given point x, let's say that I have this particular point, right? Let me just call this point x a, and this is the x-axis. Yeah, what is the slope, would somebody say, or the incline?
So the rate at which x is changing as you move along the x-axis.
Exactly. So the unit, and the rate is the unit change, the unit increase in y when we move a unit distance. So you move a unit distance along x-axis. So you go from here to a unit distance would be, let's say, delta x, and you are here. So what happens is you reach here. Now what you notice, this was your y at a, this is your y at a plus delta x, little bit. It's a function of a different point here. This point is x a, or sort of x, well, I should have said xa rather than a, but let me call it just a, to be succinct. So it is a plus delta x, this point, right? And so at this point, you have this. Now, how much increase did we have of y? Oh, look at this. This is the jump in y, isn't it? And it is therefore slope here is. And so let us say delta x is equal to some form of 1 unit. Right? You're a little ant and you walked 1 unit along the x-axis. The slope here is simply y a plus delta x at the new location. And let me just say the unit 1, if you want to think of it as 1 here, minus y a. So if delta, so for delta x is equal to 1 unit, it's the unit increase in your, how much did you increase? So not the unit increase, it is the increase in y that you have. So this is your delta y, the increase in y for just a little bit of moving forward with it. And now what happens is that people have different notions of units. And this delta x, which we think of it as a unit movement, is not what you would say. Let's say that this is given in miles. Right? So you don't think of delta x to be 1 mile. That is too much. Those of you who have been hiking in the hills, you know that the slope changes vastly over a mile. So when you talk of unit distance, you mean a very small amount. So if you're measuring in terms of mile, you would say, well, 0.001 mile or something like that, right? So people in this space, they say, make sure that your notion of unit distance is that of an ant, right? A very small amount, right? And so if you're using a much bigger yardstick, you have to declare slope to be delta y, the change that happened, and in terms of your unit, what was your yardstick? What was 1 unit movement? You know, we don't want to walk a mile. We want to walk a tiny amount. Let's say 0.0001 mile. And we want to see how much we moved up, maybe 1 yard, or maybe we just move a little bit up a hill, and we see how much altitude we gained with that. That's your slope. Right? So that's the basic notion of slope. It's the increase. Now, this is a obviously a refresher. So, but I'll just ask this question. At A, is the slope positive or negative?
Positive.
Positive, right? So the way that people say, so what happens is that there's a notation for slope. I said this delta y, delta x. So people's notions of deltas can be big and small. Some people may think of delta as a mile, and that's unacceptable. So mathematicians have come up with the notion of delta. They say that slope is not any unit of delta x, but it is really, so this is approximately, let's say, the exact definition of slope is that you take this limit of delta x tends to 0. In other words, what is the tiniest little increase that you can make? Right? The tiniest possible step that you can take, and you go and measure how much did you gain in altitude. And they refer to it by a notation, dy or dx, where dx, the d of x says the smallest possible increase of x, which is greater than 0. Right? People often use the word, I don't want to use the word epsilon, because epsilon in machine learning we often use for error. So epsilon, mathematicians have an interesting concept, and they define it in a sort of a very odd way. They say epsilon is a number greater than 0. Well, that is fine. So what is it? Well, it's also a number smaller than any number that you can think of, positive number you can think of. Now that becomes problematic. Suppose you thought 0.0000000001. Well, they will say, well, epsilon is smaller than that, right? And you can keep going that way, but it is still greater than 0. That's how we think about it. It's sort of a logical concept, not something that exists in real world, but it sort of clarifies the definition of a slope in an exact way so that two people don't disagree with each other. So that is the slope. Now, slope here, we'll say that dy dx is at A is greater than 0, isn't it, guys? This is what we observe at this point. What about point B? At point B, oh, sorry, not B, this is not B. At point B is here, B. And if you move at B a delta x step, so that you go to, you go here, and again here, delta x to this point. So you go from this to this point, your y goes from y, b to y, b plus delta x. So which is bigger? Have you increased in height, in altitude, or decreased in altitude, guys?
Decrease.
Decrease.
Decreased. And so the slope, you say, is negative because you did not gain. Slope is always the gain in altitude. So, well, you gained a negative amount in altitude. So you would say at B, this is true. Make sense? And now we ask this question. Suppose you have to find the minimum point on this function, of this function. And you are a little ant. And quite literally imagine, so by the way, think of this as something very real. Think of it as a peculiar children's slide. They slide from here and they can go all the way there, and the other way around, or you can slide a marble and it will roll back and forth. So now think about it this way. Suppose your goal is to find the lowest point of this function, of this slide. Now we ask ourselves, how do we get there? Well, you can say very quickly that, well, it's very easy to get there because we all know that at the bottom it's flat. Do you see it is flat? The slope is, you're neither gaining altitude nor losing altitude. You are basically in the bottom of a bowl. Are we making sense, guys? So
Yeah.
you can say that at minima, and I'll write it here, some things, at minima, slope is dy dx is equal to 0, right? And given life's imperfections in data, you may modify this and say it's approximately 0, and that will give you the minimum, right? So now the thing is, well, why, if you have to find this, you could just solve for this equation and do that. But it turns out that you can't actually in real life, because this curve that I showed, and now I can make it into a surface by spinning it around on its axis, then it will look like a bowl, right? A parabolic bowl. But and then you can generalize to higher dimensions from there. But look at this. This is something people call a convex surface. What's a convex surface? Something that has like, so first let's define something, convex. Convex surface. In this case, a convex curve. You say that a curve is convex if you take any 2 points, any 2 arbitrary points. Let's take this and this. Let me call this P and Q. Then the line joining PQ is such, it's called the segment, that the curve that is there between P and Q will always fall on one side of it. So you can take any 2 P and Q and you will find that the curve never intersected. The function never intersects any of its segments.
So as if this property is only for a curve with one bend.
Yes, or surfaces with just one bend. Yes, that is true. And that is what intuitively, that's what convex means, right? Or as my mathematical daughter was joking, a convex is Papu's tummy. One bend, right? So anyway, so it's a joke, of course.
Can you repeat why, how?
See, convex
surface.
is bulging, right? One way of thinking of convex is it's bulging. Think of a convex lens. Now you may say that when you think of convex, people often think of concave. They say, well, I can think of this as concave if I'm sitting here and convex if I'm sitting here. So what does it mean? So mathematicians say that irrespective of where you are sitting, this function, this curve, is convex if the following property is fulfilled. Intuitively, if there's a uniform bulge, right? But like a balloon's bulge. But mathematical definition that achieves the same result is this. I pick any 2 arbitrary points on the function. So I picked P and Q. Then the curve, the part of the function that is between P and Q. So which part is there? It is this part. This part, isn't it? And then which part is the segment joining the 2? This part is the segment. Oh, sorry, yellow. This part is the something fishy here. Where is my okay, I'll just take a different color. This part is the segment, isn't it? And this is the part of the curve between points P and Q. So do you notice that the curve, the pink does not go, I wish I'd chosen a different color. Pink does not intersect with the red. Is that clear? Let me illustrate this with a counter example. So look at this curve now. Let us ask whether this statement is always true. If I take this 2 points, A, B, then it is true. This curve is not intersecting AB, isn't it? But likewise, I can say between this C and D, it is not intersecting. But the moment I look at this, so C and D is fine. But what about what happens if I take a different point? I take, sorry, guys, give me a moment. Yes. So suppose I join these two. CB. Now look at the segment CB. You are able to find one segment, and you'll be in fact able to find many segments. Now, do you see the curve intersecting the segment? Guys? Do you
Yes.
see the curve crossing over the segment?
Yes, sir.
Correct.
Yes.
It is, in fact, oops, oops, 2 points. So this is not convex. So I'll just put it like that, that this is not a convex
Local minima.
curve, right? So the intuitive idea of a convex curve is it has, like Premjit, I believe, said, that it has essentially one noticeable bend. Are we together? So when you have one minima, one bend, only one bend, it is easy to find a minima, right? Especially if it is looking like this. The trouble is when you have a non-convex surface, life gets a little bit harder because there are so many points at which derivatives are zero. This is bad, this is bad, this is here. There are many things. And not only that, computing this derivatives directly and setting it to zero is computationally quite brutal. It sort of involves, this is a numerical aspect, it involves matrix inversions, and they are bad for many reasons. They are quadratic in the number of instances and the feature sets and so forth. They are slow, they are prone to failing, and what many other things. So people in numerical computing, they do sort of what is called pseudo inverses. They try their best not to get into situations where they invert matrices. And in practical terms, when you have vast amounts of data, it's not generally a good idea. So there is a better idea of how to find this point, this minimum point. How do you find that? And that trick is something quite interesting. I will ask you to note one thing. Suppose you are here, you are an ant here. So how does an ant look? Is that an ant in a flake? So suppose this ant is here at B and wants to go home. This is home, right? So ant is saying the same thing that Dorothy says in The Wizard of Oz, no place like home. So she has to go home. So how does she go? From this point, in which direction should she go? In this direction, right? She should make a journey like this. Does this make sense, guys?
Yes.
The only way you can come home is this. And what it means is you make little steps along this direction, so that you end up here. You want to move in this direction. So now let us see what it is. But you don't want to keep moving. You know that at some point you have to stop when you come to a point where the slope vanishes. Right? So you want to take a step based on how much the slope is. If it is steep, you tumble down more. If it is not so steep, you begin to now go slower and slower because you are getting closer to home. Right? Very much like your car. You don't drive at full speed towards your home, you slow down, right? So then if you look at that, what you're doing is you're saying my new position is the slope, based on the slope, is proportional to the slope, and you take a little step, delta x, right? So I will just simplify this step, delta x, in our context. I will call it, and there's a fancy word people use in this literature, they call it the learning rate, how big a step you're willing to take, learning rate. Why it is called the learning rate, we will learn in a while, but this is your delta x, and it is denoted by the symbol alpha. So I'll write it down. Learning rate, delta x here, is learning rate usually given as alpha. This is the notation that people often use in this space. So alpha. So we know that if you take the slope and the product of these two, well, this is proportional to here, then the product of this would be a good way to decide how, like you keep taking alpha step, but you multiply it by the slope, because when the slope is high, you want to take a bigger step. When you start coming close to home, the slope is small, you want to take a smaller step. Otherwise, what will happen is you won't know how to stop. You'll keep moving forward in the other direction. So by multiplying it by slope, you're modulating yourself down so that you slow down and you reach home. But now the question is, I am here at B. To go to this point, how do I go? So what should be my B next B? Let me call this B next. B next is equal to what? Now think about it. It is your previous B, you are here, B. Now what do we do? Let's look at this. We know that we want to make a step like this, of size this, but slope though here is negative. Slope is negative. So we don't want to subtract this quantity from this. In other words, we don't want to move in this direction. So how do I go in the forward direction? If the slope times alpha, alpha assume is always positive. And one easy way of thinking of alpha is, like I told you, think of an ant that makes very small steps. 0.0, like alpha is 0.001. Tiny steps that an ant is taking in terms of your yardstick. And it is always fixed. Let's say that for now, it's always fixed. So when you multiply it by slope, you end up with a negative number. But you want to go B next relative to B. Is it greater than B or less than B in this situation, guys? This is B, and B next. Look at this. Is it greater than B or less than B on the x-axis?
Greater than.
It's greater. So to go to B next, surely I have to add a positive quantity. But I have a problem. Slope times alpha is negative. So how do I make a negative quantity negative? Well, it's very easy. You multiply it by -1, isn't it? So suppose I did this, slope times alpha. What about this now? Let's look at this equation. The next value of B is B minus the slope of times alpha, this factor, modulated step that I take. Now, minus will do what? What will this minus do? It will, would you agree that it will make you move forward in the positive direction, isn't it, guys?
Yep. Yes, sir.
Yeah. And now, likewise, let us look at what our life looks like if we started out at this point. Okay. So suppose you are at A, I'll color A. Right? Is this green coming across, or you should use some other color? Oh, sorry. I will just be a little bit more careful. Suppose this is A, right? And you want to go, actually, let me just do it this way. Let me leave A here. Suppose you are here. Which direction do you want to make a step in? You want to go home, you want to go like this, right? Do you agree that you want to go like this? You want to tumble down this hill. So in order to tumble down this hill, you need to make your next A, let me just call it A next. Let's think about it. A next is, let me take a thicker one. A next. What do you expect it to be? Your A next here, do you expect it to be bigger or smaller than A?
Smaller.
Smaller, right? So let's say, what do we do? A. But now look here. What is the slope at this point?
Positive.
Positive. So what will be your slope times alpha? It will be positive. So you want to subtract slope times alpha, isn't it? If at A, you want to do this because slope is positive. Your modulated step to make it backward, you again want to subtract from it, right?
Sir, I have a question.
Yes.
Slope you said is dy dx, and then the learning rate is dx. So when we are
Learning rate is the tiny alpha. Yes, go ahead.
isn't it dx?
See, when you say dy dx, no, you don't think of, well, think, okay, all right. Let us say that it is, see, dx, when I see delta is different from d. D, remember, is very, very small. One very easy way of thinking of it, very small. In fact, this notation, right, this is an abuse of notation. What you mean is it is basically limit. It is not dy divided by dx. So it is not that this is actually a quantity and this is actually a quantity. People think of it like that. And there is a guy, mathematician named Leibniz, and he said, if you do that, well, it turns out that it's legal. You don't get into trouble. Things do make sense. But remember, delta and d are different. Delta is a reasonable step. D is the tiniest possible step you can imagine. So our alpha is not d, because d is so small that it is a billion times smaller than alpha.
Got it.
Remember,
Yeah.
billion.
Yeah.
So you think of it like that.
So they will not cancel out each other.
They will not cancel each other, right?
Got it.
Slope, see, think of it. Slope is the tilt, right? Is the incline. And based on the incline, if the incline is high, you want to take a bigger step. Like basically your total step, suppose your legs, so think of alpha as the length of your legs. So you know that when you are really steep and you take a step forward, what happens? You end up taking a much bigger step in a hill, downhill, than when you're walking on a flat surface. Right? So think of it like that. The slope times alpha becomes what you actually come down when you are on a hill. So now, guys, notice that both yellow and green, these equations, do they look alike? Whether it is in terms of A or B, do these equations look alike, guys?
Yes, sir.
Yes. And so you make a rule, from that you generalize, and you realize that the rule is that on this curve, so let us write down the big rule we discovered. I'll write it in one new color here. Rule that we discovered. Rule. For the ant to go home, all they has to do, that wherever the ant is, let's say that the ant is at X, right? Any arbitrary point X, the X next has to be X minus the current value of X minus alpha, well, slope times alpha. Let me write it this way, because times alpha. Does this make sense, guys? So this rule, what does it help us do? It helps us come down a hill. And it has a very simple intuition. Now think of a two-dimensional surface. Now this will look like the hills around your house, right? In Bay Area, we have a lot of hills and we go hiking. So if you want to come down the hill fastest, what do? You take the path of the steepest gradient. Wherever the slope is maximum, you take that path. And that is what this rule is also saying. It is saying that, well, in a two-dimensional, in a simple curve, there is only one direction that you can come back, tumble down. But when you have more dimensions, a surface, you take that path, the steepest path. Think of the slope being the place where you come down most. And the generalization of the word slope to higher dimension is gradient. Right? So remember, so gradient, the word gradient, and I won't go into the mathematics. We have covered it many times in our past workshop, and I'll again cover it on a Saturday. Gradient. The gradient of X is generalization. It is the generalization is df dx generalized to multivariate higher dimensions. Higher data. Are we together? Well, that is a long discussion, but now let me come to the meat of the matter, because, so that we can get started with our lab. So now what happens is, how does it relate, all of this discussion relate to the loss function. Let's get back to our loss function. Our loss function is a function of the weights. So it exists in this hypothesis or the parameter space of W0, W1, etc. Let me just say and assume that there's W2, etc. And this is the loss on the weight. And what happens is that in this surface, if it was very simple, then you could have a surface like this. But in general, convexity is not preserved. In neural networks, you don't have convexity. Like the surfaces are more like this, curvy, like, you know, with many, many minimas and maximas, local minimas and maximas. But in any case, a path of gradient descent helps you find the best value. Your W star is sitting right here. Right? And if you look at these projected down, you see these contour maps, and we'll play with that in a subsequent lab. That will be an extra session because we need to move forward. And I'll show you how you can draw out these contour maps and see a gradient descent happening. So this thing we do a gradient descent on the loss function. And that essentially summarizes it, guys. If you ask yourself in predictive modeling, that is regression and classification, what is learning? Learning for predictive models is nothing but a gradient descent on the loss surface. That's a very powerful statement, guys, and I want you to think over it. If you don't understand it, we'll cover it again on Saturday and we'll clarify it. But at this moment, I hope you get some flavor of it. We do that. Now, this leaves open one question, that when you find this alpha dot gradient, how do we find the gradient? How many points do we take to find the gradient of this loss function? Because remember, loss function here says, let us recap what the loss function said. The loss function said, and what we are searching for is arc min W star, basically W, that's your W star. And I'm bringing back memories of what we did a while ago. Arc min loss of W, which is the same as, just remember this, I is equal to 0 to the number of points. And this is your y minus yi minus yi hat in whatever form you write it, plus regularization terms. So now pay attention to this guy, n. How do we, this, you realize that if you find the gradient of L, this n is implicit. You can find the gradient, but it depends upon how many points you have taken into this loss function. The choices are, there are many choices actually, and those are the three choices we'll talk about. Suppose you have, okay, sorry, let me draw it out a little bit. So let us say that your data set is, I'll put it linearly there, right? This is your data set, and it is made up of samples, 1, 2. Think of it as a nice bread that you have sliced into slices. And for some of you, it is morning time zone, so you must be getting hungry for bread and breakfast. So it's like that. Now, each point is a datum, is one instance of data. So while learning, when I'm doing gradient descent, I can take my n to be 1, just one data point. I'm saying find the gradient, find the slope with respect to just one data point, and then take a step. What is a step? When we do this part, W next is equal to the current value of W minus alpha times, and now I will write the slope in a more, this peculiar inverted triangle notation of loss. If you have difficulty remembering the inverted triangle, I often say that think of the pyramid, and you can make the pyramid more useful by turning it on its head. You get the gradient. I'm joking, of course. So here we go. This is your step, one step. So in that one step, you can take n is equal to 1. That is, when you do that, it is called stochastic gradient descent. It's a name at this moment. We won't get into all the details of it, but just say, think of it as just a name of this fancy way of doing things. If you take n is equal to, well, the total size of the data, let the data set, let the total training data size be, what do we want it to be? T. Then when n is equal to t, it is called batch gradient descent. And the name is sort of unfortunate. It basically says that, I suppose it may at some point have referred to the fact that you're batching all the data into a single batch. You're clubbing them all into a single batch and then computing your gradient. This is your batch gradient descent. So that is taking all of it, all t of this. Let me just say t instances, all t instances. And then there is a third possibility that you have, which is that you take a number that is somewhere in between. Let me call this little n is n, and it is between 1 and t. Usually, n is much less than t. In other words, much smaller than t, but greater than 1. Because if n is equal to 1, you get back to stochastic gradient descent. So when this n is equal to this n, and values of n are typically 2, 4, people tend to, just by convention, pick in powers of 8, 16, 32, 64, 128, and so forth, right? Pick one. Something like this. So then what happens is one step is learning from a 1n. So it is learning from a batch, one batch. Let me write it. N items makes, the technical word is actually mini batch. It's a mini batch because, batch has unfortunately gotten reserved for the entire thing. And so you'll see very confusing terminology in the library. So I want to clarify it. It's a mini batch, right? N items makes a mini batch. So how many mini batches, how many total number of mini batches there will be?
T by n.
Yes. T over n. And so how many steps you will take by the time you run through the data? Running through the data through, let me just use a shorter form of this, through the data once, while learning, you say that you have completed, you use a word, you say you have completed an epoch, right? Once is said to be completing an epoch. Are we together? So now one epoch in mini batch will have a T over N. So steps, because you're going to, there's so many mini batches there. Sorry, I apologize. Just scrolling. Since there are, so for mini batch gradient descent, number of steps is equal to the number for each epoch, number of steps is equal to the number of mini batches, and that is equal to T over N, right? In the case of stochastic gradient descent, what is the number of steps per epoch?
T.
T itself, because every data point is a step. Right? So this is the distinction between stochastic gradient descent, batch gradient descent, and the word for this is mini batch gradient descent. Now, there's more technical aspect to it. It turns out that if you just do any one of these, there are different implications. I'll give you an idea, but we'll cover this in the theory section later. If you do stochastic gradient descent, you tend to be wandering around in search of home. You get to home, but you sort of, it's almost like, imagine that there is a breeze, a strong breeze or something. And so as you find your way home, you go, well, not a breeze, it's not a good example. Imagine that your way home involves coming down a rocky hill. And so you take a path, because on a bumpy hill with many, many different gradients, the path that you will take to get to home will not be the straight path, right? You will wander around. And even when you get to home in stochastic gradient descent, it's sort of you wander around the home. You wander around the minima. On the other hand, with batch gradient descent, you have a more sort of a direct path home. But the trouble with a batch gradient descent, this one is, it is very hard to fit that much data into the memory. Neural networks work best when you're talking of millions or billions of data points. And even with millions of data points, each data point occupying quite a bit of bytes, it doesn't fit into the memory. So batch gradient descent often turns out to be impractical. With small data sets, you can do that, but for large data sets, it's impractical. So what people do is, between the fact that stochastic gradient descent is a bit slow and you sort of meander around the home, or you gradually get to the home, you don't take a very direct path home, and batch is not feasible. What people do is an in-between thing, mini batch gradient descent. That's what you do in practice. In a mini batch gradient descent, what you have is, you take smaller steps. You pick n of a batch of 2 data points, 4 data points, 8 data points, and so on and so forth, right? So this is it. So guys, this is the foundation we needed to do our lab. Now, I'll just summarize what we learned, and then I'll take questions. It's important we understand that. To understand the code. Today, importantly, we'll learn to write our first neural networks and do something of value. So the rules is regression, let's say, is like learning in regression. Basically, let's take the regression problem. Classification is not very different, but we do this. First, you have the loss function. When you have a loss function. Here, what did we did? We took the basically 1 over n yi minus yi hat squared summed over n. Well, let me, this is abusive notation. 1 over n sum over I is equal to 1 to n, where n is not the total number of data, but the size of your batch, mini batch, right? Now, there is a word for it. Do you notice that you are squaring the errors? This is the error term. So you have the error terms. What do? You square it. You take the errors, you square the errors, and then you sum it. Well, you sum it, and then you divide it by n. So when you take a bunch of items and you add them up and divide by the number of them that you have, what are you computing? You're computing the mean, isn't it? Mean of square errors. Does it make sense, guys? You're squaring the error, and 1 over n over all of those errors is this. So that is the average, right? Average or mean, average squared errors. And so the name for this is MSE, mean squared error. That is your loss function that you have done. At this moment, even though there's a regularization term, people tend not to mention it. It's assumed that there will be regularization terms there. So they look at the first term, the main term, and they say that for regression, an effective loss function is the mean squared error loss function. That is not the only loss function. There are other loss functions, but let's discuss that in the theory section when we do it more in detail. So loss function, and then you have to take steps. You talk of mini batches. You talk of mini batch, n. You talk of epoch, right? Running through the data once, right? And so your learning is you go step by step, you do gradient descent. These are the core ideas that we will use now in machine learning, in AI. And in fact, these are the main ideas that will carry you through foundationally throughout the workshop. If you have grasped this much, you have actually grasped a large part of what we are going to do. Right? So from that point, it was a little bit conceptually heavy, but if you have questions, ask me. I'll just review it. So I'm saying that when you try to fit, for example, in the case of a linear regression, it's easy to understand, a line to data, your reality and predictions will differ. The gap is the error. One way of capturing the mistakes you make, amount of mistakes you make, is called the loss function, is you square those amounts for multiple reasons. One is squaring makes it positive, but there is more reason to it. There are some good amount of mathematics. There is a theorem that actually called Blue theorem, which says that it leads to the best unbiased linear estimator. Right? But we'll leave all that there. So squaring is a good idea. You could have gone to the fourth power, for example, or you could have just taken the absolute value of the error. That also is valid. And people sometimes use that as a loss function, but we'll stay with the familiar one, some squared error. Right? So you do that. So how do you minimize the error? The mechanics is the gradient descent. And I explained the concept of gradient descent. How do you come down a hill? You go against the slope. So one way, sort of a way of thinking about it is that in the space of functions in the mathematical world, in many ways, you can think of it this way, that there is always a Google map to take you home. And that Google map is the derivative. If at any given point you can take the slope, you can determine what slope there is locally, how tilted the floor is locally, you can always find your way home. Right? That's the basic intuition of gradient descent. Just go against the slope. In other words, go in the direction where slope would increase. And so, of course, you'll start coming down and down and down. It's a very obvious intuition, and ultimately you'll hit home being the minima. Right? So that is all there is to gradient descent. And we do it in small batches. So I would like to take any questions, and then we'll take a 10-minute break. Any questions, guys? Are we following this much? Those of you who did ML100, 200, of course, this should look like a very familiar review, I hope.
So Asif, so there will be multiple nodes in a layer, right? So this optimization or the minimum weights will be found for which using this method, like for individual node, and then
remember, we are not talking of neural net per se. We are saying that if you're doing regression, and imagine a box that somehow you want to do whatever the parameters are of that model, W. It may be simple linear regression. It may be neural net, and neural net has lots of weights. But what we want to do is we want to find the W star, the best weights. So we have to do a process of a gradient descent. We have to first find the gradients everywhere, right? Of the loss function everywhere, and then take the step. Now the question is, how do we find the gradient of the loss function everywhere It's then there's more trick to it. Layers make it a little bit harder because for reasons we'll do that. Then you use the chain rule of calculus. If A is a function, like f is a function of x, and then g is a function, like y is some function of f, then it is implicitly a function of x, but indirectly. So that is how layers behave. Layers are just looking forward one step at the layer ahead of them, and they're looking one step backward at the layer behind them. So we have to figure out that if a layer in some sense is only locally aware, right? In the forward direction, it can do multiplication, it can take back gradients. Then how do we do a global step forward, learning step forward? So that is a topic of back propagation. And we'll deal with the back propagation in a better. But at this moment, forget that. For the sake of today's lab, because I want to give the majority of the time to solving problems, just think of it this way, that gradient descent is the step you must take, right, to improve your W, your weights. With a bunch of data, you take, with the help of a bunch of data, you take one step forward in the right direction. Are we getting that, Abhishek?
Yeah. So this is happening for each node, right? Is each node in one layer?
Yes, it will be happening for each node, in fact. It will happen for each node, but how it happens, there's a little bit of a complexity there, but think of it like that. Every single weight, see, weights are associated with those nodes. And if you have layers and layers of nodes, and each layer has hundreds of nodes, you're really looking at a huge number of weights. And we'll see that immediately. Huh? We'll make some drawings and we'll see that. So actually, why don't I draw and show it to you guys right now? So suppose we'll take one input, right? It goes to even, let's say, 3 nodes. And those 3 nodes go to 3 more nodes. And those 3 nodes go to an output node, right? Let's see how many interconnects we can have. This can go here, this can go here, this can go here. This can go here, this can go here, this can go here. This can go here, here, here. So what happens? How many combinations are there? 3 cross 3. 3 possible sources and 3 possible destinations. So there are 9 weights in this region between the 2 layers. Then here there are 3 weights. And then there are 3 weights here. Then we add a bias term to each of these. Those are also parameters that we want to learn. And so what you end up with is 9 plus 3 plus 3, 15, 16, 17, 18, 19, 20, 21, 22. You're looking at some 22 weights or parameters. So you have a 22 dimensional space in which you somehow try to do a gradient descent. Are we getting that?
Yeah.
That's it. Huh?
Asif, can we do a quick recap on what you have mentioned when you said lasso and ridge?
Oh, for Premjit, forget that. Let's do it on Saturday.
Okay, so that's not connected, right?
Yeah, it's not connected. We don't need it.
Okay.
Need it for today's lab.
So how do we know the number of mini batches?
Oh, you never know. It's a hyperparameter of the model. Oh, number of mini batches, the total data size. Suppose, here's the thing. In reality, right? Let's say you have 10,000 data points and you set your mini batch to 32 or 16. Now, all you do is divide 10,000 by 16 and whatever number comes through is the number of mini batches. The last mini batch will be slightly shorter than the other. You realize, right? So think of it this way. Suppose you have 10 data points and you take a mini batch size of 3. So what will happen? You'll get one mini batch of 3, another mini batch of 3, another mini batch of 3. And the last mini batch will have how many elements? 1. You see that, right? That's it. So how many mini batches we had? 4. Harini, got that?
Yes, sir.
That is it. think of this like that. This is the amount of data. This is the min batch size, and this is the number. That's that.
So
So
Asif,
you don't really care about the number of steps. All you know is that number of steps increases the smaller your mini batch, and they decrease the smaller the bigger your mini batch. That's all you care.
Doing gradient descent,
Yes.
so the number of batches to minimize, we should give it, or it will do it like.
No, it will figure it out on its own. All you have to tell is the mini batch size, and mini batch size becomes a hyperparameter of your model. You have to think. See, it's not really affecting the performance that much. I would say it's more a practicality question. How good hardware, what quality of hardware do you have, and how much can you squeeze into each mini batch, right? So if you have a Gorilla hardware, then sure, maybe you can take a slightly bigger mini batch. Usually people will start with a mini batch of 8 or 16 or something like that.
Asif, in terms of a conceptual understanding of the mini batch, is it right to assume that when you have a small mini batch, you're going to take a long time to complete the process?
Yes.
But when mini batch size increases, is there a chance of missing a local minima?
You don't miss a local minima, but you certainly run the chance of basically crashing the whole program. Very realistically, you'll face these things.
Okay.
On your laptops, right? It will just barf. And the last thing you want is a program that's been running for 3 days to barf. Right?
Okay. I think we have to play with it to experience it. Yeah. Thank you.
Yeah. Practical life considerations are much more important with that mini batch size. A little bit, maybe it affects the overall performance, but I don't think it's a significant contributor. So see, you have two things, right? How many epochs, how many times do you want to run through the data? And how many, what's the size of your mini batch? Both of which you have to tune. And you're realizing now that when you do deep learning, you will have all of these decision points, hyperparameters, and they keep growing more and more. How many layers do you have? What is the size? How many nodes you have in each layer? We'll think about that. And before you know it, you realize that there are too many choices or decision making to do. It's overwhelming. That is why the new subject of automated AI or automated machine learning, which in a mathematical process searches for the optimal, it looks into the search space of hyperparameters and finds the best combination of all of these considerations, all these decisions. So that's a separate topic. We'll come to that. So guys, this is it. I hope any other questions before we take a break?
Yeah,
Yes.
Asif, I do have a question. So, what I'm saying is like gradient descent is an iterative algorithm, and in the neural network, most of the time, the function we are solving, the cost function, is non-convex, and there is a high chances that my function, like I will stuck into local minima, and there are advances like Adam and RMS prof which help us. But my question is like, apart from gradient descent, we have Newton's or SM or other algorithms. Then why we don't use it, and like what's the scope, and why we are most of the time go with the gradient descent?
That's an excellent question, Naveen. Good that you asked. See, the thing is, we intuitively feel that in a high dimension space or in problem spaces, we'll have many minima, right? It will be teeming with minimas, local minimas, isn't it? But two things come to our rescue. One is the momentum that you identified. If you have a momentum, physical momentum, you bounce out of a shallow local minimum. The other thing we are discovering, and only now beginning to understand the mathematics of, actually the deep learning spaces, these worlds are not teeming with dangerous minimas where we get trapped. We thought so. People did a lot of simulated annealing and this and that and many other things they thought of. Today, actually, we don't worry about it so much because it turns out, and in the theory part, I'll give you a reasoning why. It turns out that higher dimensional spaces with complex surfaces are full of saddle points. And they don't have that many, relatively speaking, that many absolute local minimas and maximas or local minimas and maximas are relatively sparse. And there's a very elegant argument to show that. It took people many, many years to realize that that is the case. Right? And that's why just having a little bit of momentum takes you through. Most of the time you get to the true solution. You don't get trapped in local minima. At one time, people used to believe that, it's a lost cause. So people used to always, see, for the longest time, they used to always look for those methods whose loss function was convex. And people used to actually dismiss the neural network for that reason, because it doesn't guarantee you a convex loss surface. In fact, it is not convex. Why don't we do this? Right after the break, I'll show you a video where you can see simulations of the loss surface. It's not convex, it's highly complicated. But the amazing thing is they are filled with canyons, or with, canyons and creeks and, I don't know, ridges, but not local minimas and maximas. In one direction, if it is a maxima, in another direction, it is happily coming down. So those are saddle points. And higher dimensional spaces or higher dimensional surfaces, they have a huge amount of saddle points which are harmless and rather sparse number of minimas.
Okay, thank you, Asif.
All right.
One
Anyone
last
else a question before we take a break?
I have a last one question about the epoch. So epoch is basically you run one pass through the entire data. But when you say I want to run 2 epochs or 3 epochs, what do you change between one epoch to another? Because if you run one pass and then second pass through the same data, wouldn't the results be the same?
No, it doesn't work like that. See, that's a good question you asked. So guys, see, okay, maybe I'll draw this curve. This curve here has become rather cluttered. So let me redraw this curve here. Your question is, can we not reset ourselves at every epoch? The answer is no, you don't. See, look at this. You have an error surface like this. In the first epoch, let's say that your total number of steps are 4. You took a small, let's look at this data set size. 10 data, each batch size is 3. So 1, 2, 3, 4. You're here, right? This makes one epoch. Epoch number 1. You haven't reached. So when you start your epoch number 2, you're not starting from A, you're starting from B, right? So next epoch will take you here, right? Do you see that 4 steps here? So this is epoch number 2. And so 1, 2, 3, 4 with this data set that you're looking at, and that makes your epoch number 3. And maybe the 4th epoch takes you home. Epoch 4 or 5 or whatever, etc. You can go on. In one of these epochs you'll reach. So the thing is, if you don't run your algorithm for sufficiently many epochs, you're still hanging in there on a hill.
Yes.
Rafiq, are you getting that?
Yes, yes, got it. So basically, when we say one pass through the entire data, means we are referring to the entire data of a mini batch.
Exactly. All the data set divide, but each step is a mini batch. Remember, look here, this step is 3, 3, 3, 1. So I made 4 steps here in this diagram, if you can notice that.
Yes.
Right? This is a step 1, step 2, step 3, and this one is step 4. And it repeats in each epoch, those 4 steps will repeat. And one more thing you do, just for fun, is before you run an epoch, you just shuffle the data. You just make sure that the data is not somehow pathologically ordered that will screw up your learning. Right? You shake it up a bit.
So, Asif, you're saying in every epoch, you're going through the entire data set.
That is true. Let me say that statement again. In one epoch, you touch every instance of data once and only once, and no less than once. I hope this removes all ambiguity now. An epoch is whichever way you do it. You do one data instance at a time, you learn in small batches, or you learn from all the data at one single go. But an epoch is finished when you have visited or visited or touched or visited every instance of the data, and only once, no more than once, and no less than once. Right? So that is the definition of an epoch. Are we together now, guys?
Yes.
Any other questions, guys, before we take a break? So today it will be a bit longer session, guys. Is it okay if we stretch out till 10:30? Because we have a substantial lab to do.
Sounds good.
Yeah. All right. See you guys. It's 8:36 by my clock. So let's meet at 8:50 in 15 minutes. Let's go have our dinner and come back.
Yes, sir.
When you finish, just make sure that you record from the end, because I'll have to drop off around 10.
I'm sorry, you said something?
Yeah, I was saying that if you go beyond 10, then just make sure that that is recorded, because I would be dropping off around 10.
Yeah, you can then catch it up on the recording. So guys, I'm going to pause the recording for a bit and we'll meet again in 15 minutes. All right, guys, it's 8:50 by my clock. I would like to get started. Are we all back? Are you guys seeing my writing pad? Yes, excellent. Any questions before we start? So guys, we are almost ready to get started with the lab. There's one more thing I wanted to do. Today, we are going to deal with one neural net architecture. It's a very interesting architecture. It is called a feed forward network. It is also called like densely connected network, or simply DenseNet. Right? These are words that people often use for it. And it is, in some sense, the simplest notion that we have of a neural net. What it comprises of is you have some inputs coming in, x1. Let's say that there are a k predictors. You know, it is r to the k. Data comes in from here. You have, so you call this the input layer. This is just your data coming in, and then to the first layer, basically, this is your input. You have the first hidden layer, and each data, so suppose you have x1 to xk, right? Let me just simplify it for the time being and make it just x1, x2. So what will happen is both x1 and x2 will go to each of the nodes. And this, and you get the idea, right? You notice that both the signals, input signals x1 and x2, which are the two components of the x vector, and let me make it r square here for this case, will go to every node in here. Now these nodes, what are these? These are the magic boxes. Just as a reminder, each node is our magic box, or simply put, is a model. It's a model in its own right. It's a tiny model of data. It was a logistic unit, if you remember, for, for one thing, is a tiny model. Right? So if you remember, the way we envisaged it is that the weights come in, the inputs go in, the weights are there, and then finally there's a distortion function. Some sort of a activation function is here. This is what we learned the last time, right? So that is all. Each of these nodes is made up of those two things, right? Then suppose you have another layer. Then what will happen is all these five, the outputs of all of them will go to each of these nodes. So what happens is, so look at this. And I'll deliberately use a different color to signify things going to the next node, second node, because otherwise it gets, so sorry, going to this second node. Let me just do this, second node, and this goes to the second node. You probably get the idea of what I'm going at. The third, everything is going to the third node. By now, you realize that there are way too many connections out here. 1, 2, 3, 4, 5. Can you see how dense, intuitively, how dense it feels? Right? The number of interconnects. If you think of these as threads going from here to there, you pretty much are weaving a fabric in between. It's a pretty complicated set of connections. And it sort of continues. So there'll be many layers. So this is layer 1, the second layer, and then there could be the nth layer, right? And this whole bunch of interconnections will go. And typically, in the case of regression, the simple regression that you're looking at, you will have one output layer, right? Because it would be connected to this like this. Now, this output layer is very interesting in the sense that it is whatever signal comes here. Let's say that a signal, I would call it yi minus 1. You know, these is 1, 2, 3 come here, and there are certain weights here. Here, the activation function is just 1. It doesn't do anything to the signal. So in other words, it just takes a linear, this thing does true linear, and obviously there's a bias term going in, regression. In the traditional sense that you have learned from me, the linear regression, it just is doing a simple linear regression. W dot x, W dot the x coming from the previous, coming from this, not the original x, let me just call it u, let me just call the output of this layer as x to the L. So W dot XL of the previous layer, that's all. And that becomes the output. The final Y is nothing but this. So you have to ask yourself, what does this give us intuitively? So what it says is that all of these layers, and this refers to the talk that we're going to have on Sunday, they somehow distort the input feature space in such a way that afterwards, the solution becomes a straight line in that deformed space, a very simple straight line in the deformed space. So sort of the conceptual background to it. I won't talk more about it. I'll just leave it because that's for the theory part of the class. But today, what we will do is we are going to build a feed-forward network from right using PyTorch, and we are going to train it on some data, right? Using PyTorch, and it is by far and train it on data. On data. Why is this useful? If you can do that, guys, what it means is that you can immediately apply it to every single problem that you have done with me in ML100, 200. And in realistically speaking, wherever you see tabular data, you know, data existing in columns and tables, you will be absolutely ready, more or less, to, well, maybe not in one day, but in maybe in a couple of labs, which certainly will make quite a bit of headway today. You'll be able to solve those problems now using a deep neural network, especially knowing that these deep neural networks are so versatile and powerful. You can use it for all sorts of tabular data. Are we together, guys? Right? So that's the power of it. So having said that, now I will go and look at the lab. So I'll share a different screen. So far, so good, guys. Any questions? Do we understand what a feed-forward network is? It's a network with lots of hidden layers, and each layer is connected to every node in each layer is connected to every node in the layer ahead of him and every node in the layer behind it. So that's the definition of a feed-forward network. Now I'll share something else. Let's go back to sharing a different screen. So guys, when you unzip that file and bring it into your, you fire it up with Jupyter, this is what you will see. I have added a few things. One of them is, of course, the universal approximator that you guys were talking, that I demonstrated on Monday. So everything that I showed is here. Here your homework, and I'll write it down, is to invent more peculiar functions of your own and check if the approximator is able to approximate it and how well it is able to approximate it. That's your homework for the universal approximator. I'll write down all that homework and email it to you and put it on Slack. But let's go back here. Today, we are in the business of taking our first steps with linear, we'll solve one problem, linear regression. Well, I call it linear regression. It is unfortunate. I should not call it linear regression. It is just regression. Okay, I'll change the name later on. It's regression. So how do you solve regression problems? Now here, I'll go slowly, guys, very slowly. So because this is a lab that is important and we need to understand it. So guys, this cell 1, can you guys remember what this is about? Why do we do this?
We're setting the path to our
And as
code.
we learn.
Yeah, so we can see the SVLearn library that we have in the code base. Now, what does the cell number 2 do? You notice that it's importing the torch library, the PyTorch. It is also bringing in matplotlib, which gives us a clue that we must be plotting something sooner or later. And it also brings in NumPy, the arrays. So those are the 3 imports. Besides that, you notice that I have imported some classes, two things. Now here is the convention, guys, that people follow in the Python world, and I highly recommend you follow that. If you see something start with small letters, do you notice this? This starts with small letters, little c. Generally, things that start with small letters are functions when you import them. And things that start with capital letters like this starts with a capital letter and seems to have a camel case notation. These things are classes in an object-oriented sense. These are weird. So it should give you a clue that we are going to sooner or later instantiate these classes. Now let us look at these names and see how frightening they look. One of them says simple feed forward network. Promises to be simple. Let's see if it truly is simple. The other is simple NumPy data. Well, if you are familiar with NumPy from our previous things or with pandas, this will look quite straightforward to you. This create regression data is just a helper function that will generate a regression data for us. Single variable X and one output variable, one input variable, one output variable. It will create some function and you have to train the neural network to that function. Are we together, guys? And we will see whether this is able to do it or not. Now, let me introduce you to all sorts of animals in this zoo. Do you notice that we are talking from Torch, we are importing a package called NN. Right? So that is the package where most of the neural network modules are. And do you also see we import tensor? Tensor is a generalization of an array to higher dimensions. From array, you go to matrices, and then imagine a stack of matrices, one behind the other. You're looking at a tensor. And now increase it to more dimensions. Imagine a stack of tensors, and that too is a tensor. Right? So that is what a tensor is. It's a multidimensional array of some sort. Now, AutoGrad. Actually, I don't need this. Let me remove this. I should have. This is actually part of the old API that has now more or less, it's a legacy API. And I was going to use it, then I realized I shouldn't. Okay. Then what is this? MSE laws. In terms of the discussion that we had, could this be something that reminds us of something we studied a moment ago? What does this remind us?
Loss function.
Mean squared error loss function. So the loss function that computes the mean squared error. In fact, that's exactly the one we deal with in regression, isn't it? When you do regression, by default, we choose MSE loss unless there's a reason to choose something else. Then comes these ADAM and SGD. So without going too much into the details, because optimizer is a topic in its own right in the theory side, think of this. SGD stands for stochastic gradient descent and ADAM. But take these words lightly, because when they do SGD, you can still give it a batch size and so forth. It isn't what we studied in a literal sense, where batch size is 1. Right? So it's a little bit of an abuse of name, but it's a pretty common abuse of name that's been going on for the last 10 years. People create libraries and call them SGD in a very loose sense. We'll leave it as that. ADAM actually is at this moment, is one of the best optimizers you have. Think of it as doing the gradient descent. What is an optimizer? It does the process of gradient descent on the loss function. And then comes data. With data, we have a few more imports. There is something called data loader, a data set, and a tensor data. So let me now dwell on these two things: data loader, data set, tensor data, and tensor. We know what tensor is. All of computations that you do in PyTorch are done on tensors. Just as all the computations that scikit-learn does, it does on NumPy arrays. It works on NumPy arrays, which is why NumPy is at the foundation. I apologize, guys. Is the foundational data structure. We use it indirectly because we use pandas quite often. And the pandas library helps you, makes it convenient for you, very convenient to deal with those NumPy arrays and think of it in a more logical way at a higher level of abstraction. So in the PyTorch world, it is tensor. And it is very easy to go back and forth between a NumPy array or multidimensional array and a tensor. We'll see that using direct examples in a little bit. So that is one. So when you have a bunch of tensors, you then need to store them somewhere. In particular, when we do with regression, we have the training data, the input data and the output data. In scikit-learn, you usually identify it as capital X for input data, little y for labels, right? So here I'll refer to them as either inputs or data, and the output as labels or target variable or y hat or something like that. All the conventions that are common in the data science field. So that is what a data set would be. It would be the feature space and the target space, right? The labels. Now, when you have a data set, you don't give it to the compute unit, whether the CPU or the GPU, just like that, because those things don't have enough memory. Data sets in AI can be ginormous. So you have an intermediate agency which gives it in batches, mini batches, and that guy is the data loader. You can tell the data loader what is the size of your mini batch, and it will then properly go to the data set and ask for items, only as many items as needed. So it will sort of lazily keep pulling data out of the data set based on every time that your learning algorithm takes a step or asks for a new mini batch of data from the data loader, it will give it. So remember, guys, this is an interesting indirection. You don't go to the data set and ask it for a mini batch. Data set has no notion of mini batches. Data set is just data set. It knows the feature data, the input space, the input data, and the output labels. That's all it knows. But data loader is the one that will slice it up into those mini batches and serve it to you on demand. And the idea is that what do you do with that slice of data? You take that slice of data and you feed it into your network. Are we together? So how should I say it? What would be a good analogy for that? See, imagine that you have a pile of something, a pile of sand, right? And there is a machine that is laying down in your backyard, is laying down some stones and paving stones and putting sand over it. Now that machine, or maybe it's just a couple of people, you and your family are doing it. So you don't want all the sand at one go. That would be useless. You take a couple of paving stones, you put it on the ground, then you need to add some sand to it, right? So you are asking for sands one bucket at a time. It would be useless to get all the sand at once. So the guy who takes a shovel and just basically takes the sand and puts it in the bucket, or maybe a shovel or whatever it is, and gives it to you one unit at a time, one batch at a time, is the data loader. That is the basic intuition you need to carry about the data loader. Are we together, guys? So think of the data loader as the guy with the shovel and your data as the pile of sand. And your computation, your neural network as basically the actual worker, the thing that is doing something, that's paving stones or doing something. That could be one very, I suppose, real world analogy, if you want to use a rough analogy, to think about the roles of these three things. Are we together? Right? And each grain of sand there is your tensor. Make sense, guys? Right? Now, the tensor dataset thing, I don't think I use. It just is just a helper that helps you quickly create data sets. We'll go with that. So, guys, any questions before we move forward with the M4? At this moment, we must understand it, guys, because this is the beginning of deep dive. Now we're doing a survey. We understand.
Asif, here by tensor you mean an array, right? A vector.
Yes. See, a tensor could be a number, just one, or it could be one dimensional, two, or it could be, so a number is just zero dimensional. You know, it doesn't reach out in any direction. It could be a vector, which is one dimensional, right? Or an array. Or it could be a 2D array, a matrix. Or it could be a 3D array, or it could be a 4D array, and so forth. So a tensor is a general term that can refer to anything. Just as in NumPy. In NumPy, at the end of it, when we talk of an array, it could be a number, it could be a real one-dimensional array, it could be a two-dimensional matrix, and it goes on. The only difference between tensor and NumPy is actually is that a tensor contains two properties that NumPy doesn't. First, tensors can be loaded onto GPUs and TPUs, right? Dedicated hardware, CUDA hardware. The second is that tensors come with this amazing property called automatic differentiation. The derivatives, you write a function and the derivative is taken care of on its own. You feed it data, it will basically know, it will sort of hypothesize a function and it will also take its derivative. That's the amazing thing with PyTorch, and that is why you use libraries. Otherwise, if we understand the theory, we could have written things from scratch, but that's it. And you'll see that, Nisag, in a moment you'll see that, that part.
And Asif, what quality of tensor allows it to, be automatically differentiated or loaded onto TPUs?
Nisag, I would like to answer that, but a little bit we are crunched for time. Can we take that for Saturday? Because that is an open interval and we can have a long discussion then. But it's really powerful. Actually, it's an amazing thing. And I'll show you how all of this magic happens.
So one last question, Asif. Here, torch.nn.functional as f. Can you repeat what that was?
Oh, I didn't talk about this one. Yes, good. So I have to explain that. It is just a library which is filled with functions. For example, the activation function, remember that distortion function we talked about a little while ago?
Yep.
Right? Traditionally, it used to be in the F, that particular functional module. Right? Okay. And now it has been moved to the base torch module itself. So things are moving, guys. Things are fluid. As you create the next version of the library, things move around. But as the name suggests, functional. It is just built out of a lot of useful functions.
And here from torch import NN and tensor. The tensor is the NumPy thing, like NP, or is it something?
No. It is all from torch. You see that?
No, yeah, but is it like, does it work like NumPy or is it something else?
Exactly. The API is uncannily similar to NumPy for deliberate reason. They have imitated. They have made sure that it is NumPy compatible so that the learning curve that people have is very, very small.
Got it. Thanks, Sir.
Yeah, and that is the reason I took it, guys. See, what happens is we used to do this workshop using TensorFlow and Keras. Some of you have even attended a precursor to this workshop. What happens is the things that Keras can do looks very easy. Like quickly you build up layers and you do. It is in some sense even easier than PyTorch. But the moment you try to do anything non-trivial, you try to design your own network or anything like that, now it is out of the limits of Keras. You have to go to the TensorFlow API. And that API is very non-intuitive. It's a steep learning curve. You understand it. Ultimately, you can do it, but it has a very steep learning curve.
So, Asif, one quick question.
One second, let me finish this thought. So PyTorch is interesting because it follows the logical, the theory. It is not as high level as Keras, but it is certainly very intuitive once you get used to it. And you can create, that's why researchers use it heavily, because you can design very, very complicated neural architectures in PyTorch in a very intuitive manner. Go ahead, Premji.
So one trivial question. So in all those imports that you're doing there, in some, like if you go scroll up a little on the visual.
Yeah.
So there is import torch that you have, and then there is import torch.nn.functional as f.
Yes.
If you could take a minute to say why import torch didn't get all the necessary libraries. Why do you have to import certain things specifically? Is there a reason why you want to leave something out?
Yes, yes. See, languages like Python and Java, what they do is these modules roughly follow a directory structure, in both in Java and Python, to the first approximation. And so what happens is, if you include a directory, the subdirectories are not automatically included, right? Because you don't want to recursively load everything. The moment you do these imports, what it means is a lot of these things are being searched for in the Python part and potentially loaded into memory. So you don't want the whole everything to get loaded in memory, which is why one of the bad practices you see sometimes is people will do import star from, from torch import star, which means import not only that and this and that. You try not to. You try to import a thing, but not its subdirectory thing. That's a separate module. It just happens to be logically there, but it has different functionality.
Okay, all right, thank you.
All right. So now let's look. So guys, if you don't understand today, you must stop me. Yeah? It's important. So first, let us create some data. So data will create very easily. Remember that PyTorch only talks in terms of tensors. So we need input tensor, output tensor, right? The input tensor will contain, it is based of many rows and only one column. Why? Because, why one column, guys? Because we are looking at one-dimensional data, x and y as a function of x. For today, we'll keep it one dimension. Generalization, by the way, to higher dimensions is a triviality. In 5 minutes, we can do it. But let's understand things in one dimension. So it will produce a tensor, suppose the data has, in this particular case, I think I have 100 instances or 200 instances of data, whatever, I forget. So those many rows and one column. And why? Target variable. What is the space of the target variable, guys, in regression? Most often?
Numerical.
Yeah, just one number, right? It is one dimensional. So this again will be the number of data instances is the number of rows, but column is still one, right? This is what you will get. If you now, till now, I've been telling you to only read the Jupyter notebook, not necessarily to go back and look at the code of how it was created. This one, this week's assignment, your only homework is to understand every line of code that does things you don't see. For example, here, create regression data. You need to read that code and make sure you understand it. Now, I'll make life easier. I will walk through that code, explaining it, but you need to review it and make sure you understand it. Because if you get that right, you are on solid foundations. We'll move pretty fast after that. So this is it. Now I'm creating a simple feed-forward network. And what we will do is spend a lot of time looking into how we build that network. So when I take that network and I print it out, let's do that. We print it out. So what you will notice is that it produces something like this. You know, that simple feed-forward network. These are the layers. So each layer, that hidden layer or feature layer, each layer has a name, FC0, FC1, FC2, FC3. By the way, using the word FC is the FC as a symbol for it is very, very common. Most people use this variable name. so that it becomes easy to read other people's work or other people's code if you follow the same symbol. Just like in scikit-learn, if you're doing a matplotlib, you will say import matplotlib.pyplot as PLT and numpy as NP. If you import numpy as something else, let's say duck, then everybody will get confused in the middle of the code. What is duck? Right? So in the same way, just use this convention. So this is it. We have only one feature goes in. I fan it out. So the first hidden layer, how many nodes does it have?
128.
128 nodes. Bias is just the same thing. If you think of it as a logistic unit, it has a W naught or a beta naught bias term. Right? So let us, when we look at this network, this is what it is. And what I have done is, typically when you write your own neural net, it will produce this much. But I wanted us to understand more, a little bit more. So I have written a helper, a table, it generates a table, right? And some of you who come from Kira's world, there also, they have code to generate a table, nice looking table. So I wrote some code which sort of brings the goodies of Keras in case you're used to Keras and you don't miss it. So what it does is it says each of the layer, how many features go in, how many features come out, then how many weights are there, you know, how many weights. So weights will be associated here with the output or input. Where is it going? If the number of nodes are 128 and from this input fans out to each of the 128 nodes, how many weights will we have attached to the edges? One weight per edge, so makes 128 weights, isn't it? Going into the first hidden layer. So you're looking at 128 of those resistors or rheostats. But then each of them also have a bias term. Each of these nodes have a bias term. So one easy way to know how many nodes there are in each layer is simply to go and see how many bias terms are there, bias parameters are there. So there are 128 bias parameters. And so in each layer, how many total parameters, trainable parameters there are? This is the number of trainable parameters. This is what you'll learn, the neural network will go learn. Already it looks amazing, 256 dimensions, right? Then that 128 nodes connect to 64 nodes in the second layer. Do you see 64 here? They connect to 64 nodes in the second layer. So how many weights will be there? 128 times 64, right? It will be a massive number, 8,192. And 64 bias terms because there are 64 nodes in the second. And then, so this is the number of parameters, huge number of parameters. Now the third layer is smaller, 16. And how many? 16. So once again, you're coming from a feature space of 64. So 64 times 16 will take you here, right? Or 1024, right? And then when you add the bias terms, you have 1040 parameters. Now, those of us who have been doing linear regression and so forth, used to using 3, 4, 5 parameters, these numbers look astounding, isn't it? Massive number of parameters. And then finally, the output node has only one parameter, you know, just the w.x we talked about. But because 16 nodes feed into the output node, you have 16 plus one bias term, 17 parameters, right? So this is how you understand a neural network, and I'll show you the code. Is this looking easy to understand now, guys?
Yeah.
Right. And when we see the code of the neural net, it will. Now observe one thing. Do you see that these numbers are in decreasing order?
Yeah.
It is quite common for people to do that. Right? For most situations, you may start out with lots of tiny features, which help create slightly more coarse grain, higher level features and higher level features, and finally the output. So that process, and we'll learn a little bit about it. It's called representation learning. It's at the heart of deep neural networks. All of that in the theory side, but today is the lab. Right? So now what do we do? Let's go back to this simple net. We understand these two lines of code. Are we together, guys? Now comes the activation function. There are many activation functions. At this moment, we won't go into it, but the two common ones that you should play around with, first of all, is not to activate at all. That is a unit identity activation function. If you don't apply a distortion, no distortion happens. Then the second one is people call it sigmoid, but sigmoid is in the word, it's an abuse of term, but sigmoid in the deep neural network has, for better or for worse, always referred to the logistic regret activation function, logistic function. Logistic function, I see almost no reason to use because tanh, another activation function is tanh. If you just look at on the Google web, what tanh looks like, and let me show it to you guys. Huh? What does tanh look like? And yeah. Do you see tanh? It goes from -1 to +1, isn't it, guys? Do you see this picture here? This picture? I want some feedback. I hope you're understanding this. But the tanh goes from -1 to +1. Those are the two asymptotes.
Okay, yes.
Yes. On the other hand, the logistic function, if you remember, logic function, it goes from 0 to 1. Right? So they both look alike, to roughly quite a bit alike, but tanh has more sort of a area to climb, and it turns out that has a wonderful effect on learning. The neural network learns much faster with tanh. So if you want to use a distortion function, use tanh. If you want to use, on the other hand, something very simple, right, and fast, cheap and fast, and gets the work done, use something called ReLU. The word ReLU stands for rectified linear unit. Well, that's quite a mouthful. Now, what in the world does it mean? We'll learn about it later, but just think of it as a distortion function that sort of distorts the data in a linear manner. Are we together? So do you understand this question?
For the output node, can we ever use tanh, or it needs to be signaled? Like it needs to be either ReLU or something which doesn't become negative.
See, you could use, for example, a tanh. If you're doing a binary classification, people tend to use a sigmoid, right, logic, or that actually most often, and see, what happens is we get so used to using a softmax that by and large, and we'll learn about that, softmax, you just by default use a softmax. But yes, you can use a tanh for binary or a sigmoid for binary, right? And people do sometimes. I have seen sigmoid being used. I don't remember tanh being used, but certainly they should prefer tanh, frankly.
Because it will give like negative probabilities, right? If it's tanh.
Yeah, I mean, but then you can scale it up, take care of that. Generally, if you're looking at probabilities, yes, it is. You're right. What it will produce is a number between 0 and 1. So sigmoid looks more natural because it's a probability. Softmax also looks like a probability. A tanh, you'll have to struggle a little bit because it produces numbers between -1 and 1. So you have to handle it accordingly. That's that. All right. So we are at this, but at this moment, we are going to use activation of ReLU internally because it is cheap and fast. By the way, if you don't give it an activation internally, I have used ReLU, I think, by default. We'll look at the code, or I might have used tanh. We'll see.
One more question, Asif. Here, can you explain why we don't use the closed brackets after torch.gpu? Like, what is that not?
Why do we not use what?
Those closed brackets.
Oh, because it's a function. You're not calling ReLU. It's a PyTorch thing. It's a Python thing. If you refer to a function, right? The function becomes the object. In Python, functions are first-class objects. Right. So you don't need to put brackets there. So see, when you invoke ReLU function, then it might start asking you to give it some input.
Right.
But if you want to refer and save the function itself somewhere as a variable, then you don't give closing brackets.
Oh, I see. So you will use network.activation somewhere else.
Yes, in fact,
Oh,
not far off, you will see that internally when we look into the code, you will see me invoking the network dot activation.
I see. Okay.
And now let's look at the next line, guys. Loss function is MSC loss. Does this look familiar to us?
Yes.
Right? Yes. And optimizer. We need an optimizer to do a gradient descent on the loss function. So Adam is a pretty good one. Unless you have a reason to use otherwise, you could stick to Adam. Generally, you should play around. Start with Adam, and then as needed you tune. And there are many parameters to tune. Learning rate. Remember the alpha, how big steps you take. This is the learning rate.
See,
So now, yes.
In terms of the notation that you used, like torch.relu, I think that's coming from PyTorch, and .relu is referring to that function, right?
Exactly.
That's what you're setting as the network activation.
Yes.
The next line, you have loss function, which also I'm assuming by just the name, it's a function, but you're given MSC loss with brackets.
Exactly. So it's very interesting. They created MSC loss as actually a class. It is not a function, it's a class. When you refer to classes, notice the capital letter there, capital M.
Okay.
Capital M, beginning with that, should immediately give you a clue that this is a class. And it is indeed a class. So you have to instantiate a class. You instantiate a class to create an object. It's sort of the object-oriented thing.
Okay. And it returns a function.
No, it returns an object.
Okay, which is a function in this case.
Right. It returns a function object. Okay. It's basically a function object. Think of it like that. See, these are minor distinctions. See, idiosyncrasies of PyTorch. You'll get used to it. Like you say, why do the designers make it like this and not the other way around? Right? Why not make it all like, torch.msc loss? They could have. Maybe in the next version they'll do that.
Okay.
Who knows? So it's all the fun with open source, how they design it. So now let's look at this. What we are going to do is we are going to pick, oh goodness, see how many epochs am I going to run through? First, what I do is this is batch learning, batch gradient descent. Batch gradient descent. So in batch gradient descent, what is my mini batch size? Remember the word batch is abused. Batch means all of the data is the batch.
Oh, it's not mini batch.
Yes. So basically, suppose you have 1,000 data points or 300 data points. I don't remember how many I kept. All 300 points make a single batch. So one step is only one. One epoch has how many steps? In batch, come again.
One step.
One, exactly, right? Because you treat the entire data set as one batch. Therefore, you have visited it at once. Right? And so if you want to take, when you're learning, you do want to take a few thousand steps because you're taking tiny steps. So give yourself a lot of epochs in these situations.
As if you don't specify the layers here.
Come again?
In the output there, there were multiple layers, but in your parameters, you don't specify any number of layers.
Oh, where do we specify the number of layers? We'll come to that. I have not made it open in the simple feed-forward network. I have not left that choice because this is a class I created. Remember, simple feed-forward network is import from svlearn, our library. So I deliberately took 3 hidden layers, hardwired to 3 hidden layers.
Okay.
The idea is your homework is to extend it. All right.
And how to know, sir, that how many epochs to run?
So see, guys, here's a basic common sense. Whichever count not in epochs but in number of steps. you should take steps in thousands. Otherwise, you won't converge properly. Huh? And you will see this in a moment. You'll see what I'm talking about. To achieve convergence, to reach the minima, you need to take thousands of steps. So if you're running batch, then the number of epochs itself becomes thousands, because one step is one whole epoch.
Correct.
Yeah, so that is it. But hold that question in your mind, Pradeep. There'll be a more careful answer to that. You will see it on your own in the graph. So you choose the epoch. What is dropout? Ignore this. Dropout is something that helps you. It's a form of regularization. And there's a technicality to it, what it does and so forth. But pretend that you don't see this word here. Okay? Then now what do we do? Guys, we need to do this. For every epoch, we need to run through the data, batch by batch, mini batch by mini batch. Isn't it, guys? So this is how you do it. You start out, you ask the optimizer to do zero grad, means it has to reset itself. Those optimizers, they start remembering things, those derivatives, they remember from the previous run. You don't want it to remember because it can get really bad. So you tell the optimizer to go reset itself. Just as in C programming, you would create an array and reset everything to zero. Very much like that. Optimizer, reset. So this code looks new to you, but soon will become boilerplate. This particular pattern of code will literally become boilerplate in your life. This will begin to look the easiest part of the code, which is a no-brainer because it's the loop you'll run over and over again everywhere. So you take the optimizer and you reset it. Now what do? Remember, you have your neural network. You ask the network, and here's the beautiful thing about PyTorch. The network is an object, but it is also a function object. So you can invoke the network on the input data. Do you see this? We are invoking the network on the input data. Extensor. And when you do that, where did we create the extensor? Guys, do you remember we created this data here? So you ask the network to compute on X, and what will it produce? Your Y hats, isn't it? Your results of the prediction. Right? Please tell me that you understand up to this line. Anyone?
Yeah. Yes.
Simple, right? You took a network, you know that the network at this moment is useless. It hasn't learned anything. So all the weights are random weights. But nonetheless, you ask the network to make a prediction on the data. The moment it makes the prediction on the data, you know that those answers will be wrong. But what can you do? You can find out how wrong it is. That is done by the loss function. It will tell you it is so very wrong. Right? So you compute the loss.
Asif, can you define the batch size? By increasing the batch size, will you get a little bit more accuracy?
Sorry, in this one here, in this particular loop of code, we are not defining the batch size. The batch size is the entire data set. Remember, the name of this approach is batch gradient descent. In batch gradient descent, whatever is the total size of the data, that's the batch size. Are we understanding that?
Mention weights like if they're random, so they don't need to be mentioned in the code.
Come again?
So if the weights are random, like I don't see like the weights in the code, so are they not to be required to be mentioned in the code itself?
No, you don't have to. So, the beautiful thing is that it doesn't matter how wrong you are. The network, you just initialize it with random weights, and it's fine. Actually, there's a subtlety to it in the theory, I'll tell you. It must be random. You cannot make sure that all the weights are 0 or all the weights are 1 or something like that, right? It is called a symmetric initialization, and people joke about it. In theoretical physics, there is such a thing as symmetry breaking. You need it for the world to come into existence, apparently. All the forces, electromagnetic force and nuclear force to come into existence. So a similar thing happens in neural net. If you set all the weights to the same thing, initialize it to the same thing, like 0 or whatever number you want, then your network will never learn. So you initialize your network with random weights. And the the package, PyTorch takes care of it. It will automatically initialize it with some random weights. You don't have to worry.
If you tell us once more what dropout is?
No, that sentence about dropout, entirely ignore that you are seeing it.
So one more question like this, optimizer.zeroGrad.
One second, right? Let me finish that last. So dropout is something that helps you regularize your network, prevent it from overfitting to the data, right? Think of it as another form of regularization, but beyond that, till I explain it to you in a future lab. So, you know, our learning is a bit circular. We are ahead in the lab than the theory, which is why we are having all these issues. Soon, we'll get ahead in the theory than the labs and we'll be more comfortable. But at this moment, we need to make progress with the lab. So I'm bringing those things in. Wherever you see dropouts, just ignore the fact.
Okay.
Right? Now, then, all right, guys, somebody was saying something.
Yeah, so this optimizer.zeroGrad, and then the comment is like it reset the parameter gradient. So are we resetting it for every epoch, or we are
Remember, these are the gradients, not the parameters. You're not resetting the parameters, but the gradients, derivatives of those parameters. You get it? Derivative of the loss function with respect to the parameters, right? DL by dw. Those things are being reset back to 0. No, the parameters will learn step by step, but not this. So maybe I should have taken the word parameter out. Let me do that. The gradient. So those gradients are associated with the parameters. So that is technically correct, but let me not use the word. So we reset the gradients, remember, not the parameter. Now we make predictions with this network. You would agree that those predictions would be absolutely bogus, isn't it, guys? The first time you enter in your first epoch, right away, your predictions will be bogus. They'll be hopelessly wrong. So then you compute how wrong they are. Then the fact that you can, once you compute the loss, that is called the forward pass. You moved forward. You took the input. What was the input? The results, the extensor, and you forward computed the results. Now you take the results and you compute it with actually what the data is, what the training data is saying that Y value should have been. So there is a gap between Y and Y hat, right? That will help you compute the loss. So far, so good, guys. We compute the loss, and now we do the one thing that a PyTorch is and all these libraries, TensorFlow, give you. They give you automatic differentiation. They have already computed the gradients for back computation. So in other words, what you do is this step just computes internally the gradients, back propagates the gradients, but then gradients are there, computed everywhere, but you still need to take that step forward. Means all the parameters from their random value, they need to improve a little bit. In this step, you update the parameters, actually update the parameters. So this is your gradient descent step. Am I making sense, guys? This is your gradient descent step. Here you compute the loss. Here you take the derivative of the loss. You find the gradients. And here you use the gradients to do gradient descent. Right? So if you understood the part that I explained, does it feel very natural now, guys, this code? You make a prediction, you compute the errors, you take the gradient of the errors, and then you use that to gradient descent, improve. Anybody would like to confirm that this looks understandable, please?
Yes, sir. Asif, the zero grad is happening at start of every epoch.
Yes, you just get rid of the gradients every time at the beginning of each epoch.
Okay. Yeah, the rest is yeah, able to follow.
Yeah. So guys, this is it. And now what happens is the rest is just bookkeeping. I keep at each epoch, we are keeping track of the losses. How much, what was the loss? Like how much, loss is a measure of error, right? How wrong we are. That's the intuitive way to think. Loss tells you how badly wrong you are. So you would imagine that in the first epoch, when you're just entering it, you would be terribly wrong, isn't it? And then in the second epoch, you'll be less wrong and the less wrong and so forth. And we should see that in the results, we'll see. So I'm keeping the epoch, and every 100 epochs, because I have 2000 epochs, I don't want to print the improvement in every epoch. So I've taken it to be every 100 epoch, it prints out what is the loss now. Are we together? This is it. And this is the training loop. This is the heart of the training loop in PyTorch. You will always have some variation of this, but ultimately it comes down to making a prediction, computing the loss, backpropagating the gradients, then taking a step forward in improving the parameters. That's it. These 4 steps, you see it's a 4-part journey. First part is you make a prediction. Second part is you compute the level of mistakes in your predictions. That's called loss. The third part is you compute the gradients of the loss. That's the backward. And the final step is you use the gradients to improve your parameter value. That is the gradient descent. And that's it. And in those 4 steps, you summarize machine learning, at least for the supervised machine learning part. And once you understand that, I hope you would agree that it looks pretty elegant in code, right? Four lines do it in PyTorch. Now, is this code beginning to look easy, guys? Okay, let me ask the question the other way around. If you feel that you are still lost, please speak up. So to review, you need to read, I'll tell you which chapters you need to read in your PyTorch book. Give me a moment. This week's reading, and I'll post it on the Slack, of course. Everything that I'm saying, you should take out time and review it by doing chapters. So 1 is too basic, like it has nothing in it, a core PyTorch. One actually you can play around with. 1, 2, 3, and 4. Guys, definitely do 1 and 3. 2 is fun. 2 is for your own entertainment. Chapter 1, chapter 3, and then get into chapter 4. But it unfortunately starts with convolutional neural net, and it gets a bit confusing. So just glance through it, but definitely finish chapter 1 and 3 this week, guys, before we meet next time.
The deep learning textbook.
To do it from this book, right? This book, and if you have the other book, O'Reilly book for your lab, there it will be up to chapter 2. In this book, it is up to chapter 2.
Are you showing the book?
Oh, look at me. Look at my picture. Are you guys seeing this book?
Can you show the first book?
Yes.
Yeah, the O'Reilly book you do up to chapter 1 and 2. And in the Manning book, you do chapter 1 and 3 definitely, and you try to glance through chapter 4. You'll find these things now straightforward. Huh?
Sir, how the shape of X tensor looks? Because I understand you created a tuple earlier.
Yes.
But how it looks?
X tensor looks like, suppose there are 300 rows. I forgot how many rows I'm creating.
300 rows, okay, sir.
300 rows and 1 column, because X is single variable, right?
Okay. So when we are training here in network, we don't need to give the target variable?
Yes, no, we don't. That is the whole beautiful thing, right? See, it's a function. It takes the input, produces an output. Now you compare it with the actual target variable, right, to see how wrong you were for each of the instances. You see how simple it is. Input to a network is always the feature space, right? The feature vector. You don't need the target vector there. Then to compute how wrong it was, you to the loss function, you give the results. You don't give the input, you give the results and the actual value and the predicted value. Results are the predicted value.
Yeah, this loss line looks like prediction we used to do in earlier, but I was thinking that we are somehow training.
Yeah, do you see the get predictions?
Yeah.
This is predicting. So, in scikit-learn, you would say, right, some model.predict.
Yeah, yeah, I understand.
The equivalent of that is just this line.
Okay, okay.
Model
So where we train the model then in the network?
This is it. No, we are training it right here.
Right.
So think of it, the network is the model. Network is made up of all these weights. Those weights are random. We haven't trained them. This loop is training it. So let's go over it again, guys. Huh? You have a network. All its weights are junk, right? They are random values.
Yes.
So you're starting,
Yeah,
right?
yeah, I understand that.
Given the input vector, it will produce some prediction. Results are the prediction. Those predictions will be bogus, right? They'll be very wrong.
So, okay.
So now you can compute the amount of mistakes, the sum squared errors.
Yeah, that we can calculate. Okay.
You can,
Yes.
that's why I put all these comments here. See, read these comments. Estimate loss. So now you can estimate loss. Given the estimate of the loss, now what can you do? Now comes the deep neural network part. You have to compute the gradients, back propagate the gradients.
Yeah, so we will find the minima here.
It is one little step towards the minima.
Yes.
Once you have the gradient, then you can use it to do gradient descent, one step. So now what has happened? You started with the network which was rubbish, right?
Yes.
But you finished one epoch. You notice that now you're done. This is some print out and so forth. One epoch and you'll go back. But what has happened to your parameters? They have improved over the random, isn't it? They're slightly better than random, right? So this time around, next time around, when you get into the loop and you again make predictions on the data, will you make better predictions? Isn't it?
Okay. So optimizer is like a regularization thing?
No. Optimizer is the one that helps you do gradient descent.
Gradient descent. Okay.
The engine that does gradient descent is the optimizer.
Okay. Then it's okay. Yes, sir. So ultimately we will find the minimum.
That is it, right? So this is it. You get the prediction, you estimate the mistake level of mistakes, the estimate loss that you say, back propagate the gradients and take one step forward, right? In the right direction. That is it. And then you go back. Now your parameters have improved and you keep on doing it and the parameters keep improving and hopefully they are by 2000 epochs, they reach the minima and we'll find that out. So see what happens when I run this.
Yes.
Let me
can we spend some time on the backward? I think when we say back propagate the gradients, what we are exactly doing, we are adjusting those W's.
See, no, in back propagation, you're just computing the derivatives. Just think of it as at this moment, I haven't taught you back prop. Just think that for mysterious reasons, you need to know the derivative of the loss function with respect to every weight, every parameter. It's an internal thing. Right? For some reason, you need those derivatives. Right? Remember when I showed you the, okay guys, let me go back. We are going over this over and over again. I think we need to go back to our notes. See guys, are you seeing this picture? Do you remember this?
Yes.
Guys, are you seeing the screen now?
Yes.
Yes. So what do we do? In order to go, let's say from the B point here, this pink thing, to this point, and this and this and this, these are the steps over many epochs that we do. Now, at each step, for me to make progress, do you see this line? What does this say? I need to know the slope. You can't make a gradient descent step and a step of improvement till you know the slope. Do you see that, guys? So you need to first compute the slope, isn't it?
Yes, yes.
So you need to compute the gradient first, even before you can do a gradient descent step. Everything else is known. You know the previous value of the parameter, you know all other things, your learning rate, you know, but what you don't know is what is the gradient. So first, when you have the loss, using the loss, you will find the gradient. And once you have the gradient, then you can do a gradient descent step.
Yes. Okay.
Now, is it making sense?
Yes, yes. Thank you.
So we come here, and so this is what we are doing. We are making predictions, we are finding how wrong we are, then we are finding the gradients, and then we are taking a step forward. And so if we keep taking the step forward over and over again across the epochs, we will be close to the answer. And I just ran this code. Let's run this again and see what happens. Let me decrease the fonts a
You
little.
just ran it, sir.
I just ran it, but I want you guys to see it again. I'll run it again and see. Do you see this epochs run on my machine? Unfortunately, it runs too fast.
Yeah.
But so it just quickly produced all these results. So what do you notice in this loss? Do you see the loss rapidly decreasing?
Yes, sir.
Right? And here I've plotted the loss with respect to the steps, the number of iterations, the steps we have taken. And what do you see here, guys? In the beginning,
Very high loss.
your improvement is very steep, but
Yes.
gradually over different steps, it slows down. So one of the questions somebody asked is how many epochs, or more meaningful question is how many steps total? Do you realize that we, even at 1250, we are still improving. At 2000, now we are beginning to stabilize and improve a little less. But we can go on. We can go on to 10,000 steps. Actually, since this runs so fast, let's go on and do that for whatever reason. Let's try that. And if you run it for 10,000 steps, what happens? Right. Now we are running it for a very, very large number of steps. And let's see what happens. Well, it's going to go through a lot of these. And now let's plot it out. So guys, look at this curve. How does this data fit the curve, your prediction fit the data? And now let's see what happens at 10,000 steps. By the way, at 10,000 steps and epochs, your loss, do you think it's decreasing anymore?
No, it's increasing, sir.
Yeah, it is just stabilized. It's not making much of a dent anymore. So 10,000 steps were a bit useless. And your curve is still like this. Right? So what it means is somewhere along the line, you know that you should have stopped at 2,000, maybe 4,000, but no need to go beyond that. Right? So which is why initially I stopped at 2,000. So that is again, experience. You do it, you learn from it, you know how many epochs you need. So that answers your question, Pradeep. You asked that question, isn't it?
Yes, sir. And it does look like that it has to run couple of thousand times epochs, basically.
Okay. So now, guys, I'll explain the next part. What you do is, at this moment, I did not do the split between training and test data to keep things simple. So I'm just taking the predictions on the training data itself. How do I predict? Remember, this is it. I've just copied this line here. Final output, I take the whole X and then create output results. So this will be the prediction that it makes after the network has been trained, isn't it? So that's why I put the comment. Now we use the train model to make predictions. It's necessary to enter the evaluation mode. Actually, it should be a mode, not model, and exit training. So for that, you need to give this word network.eval. So when you give the word network.eval, you signal to the network that don't learn from the data. Don't try to learn from the data. So it will not do any of that autograd and observation of the data and so forth. It will just go quiet. Are we together? The network now is frozen. It's not learning anymore. And then you do this and you can save this model and all that. And this plot is very useful. You should always plot your loss with respect to the number of steps because it tells you when to stop. And then the last thing is I'm plotting the curve, the prediction curve over the data. Do you guys think it's a good curve?
Yes, sir.
Very.
Though this is a bit unfortunate, right? If you think about how I generated the data, you'll realize that I used a sine wave to generate it. So that was gradient descent, the full. How can I do mini batches?
Asif,
Yes.
so just a small question before we move further. So instead of setting a threshold value, can we determine a minimum or a maximum delta? That's like the weights value. So we don't have to run that many iterations. And
Yes, very good actually. There are techniques to do that. Yeah? But we will learn those things, Prachi.
Okay.
So, we are taking baby steps. Today is the day of baby steps.
Yeah.
Asif, one more question. Network.eval, you said it would stop the gradient from running again. Is that what you said?
It stops the weights from changing.
But won't the network be frozen anyways after all the epochs are completed?
No, no, no. What happens is that the network will continue to do, unless you call backprop, the weights won't be updated, but the computations are much slower because all the time internally, it is waiting for you to do the, it is keeping track of all the changes because it expects you to call backward on it. But you have no intention of calling backward anymore, isn't it?
I see.
You are making prediction. So it's an unnecessary overhead. You don't want that.
But don't you call backward explicitly when you run each epoch? Lost or backward?
Yes, Papa, you did. But remember, your training loop is only till here. It's over. Now what are you doing? You're going to make prediction. Maybe I'll remove this I'll split the cell. Split the cell. So this is the training part. The training part is here. Huh? This is prediction.
No, I understand that part. I'm just confused why we need to explicitly say that, okay, now the network needs to be frozen. I would assume that after
that is every time you do forward, right? That you make predictions. It is looking at how the value, the output value is there, what value it came out with, and so forth. It is getting ready to compute the derivative with respect to the loss. It's keeping track of it. It's keeping track of your loss. Do you really want it to do all of that?
Sir,
it's unnecessary. Hang on, let me finish with it. You realize it's unnecessary, right? And now you are in the inference mode. See, you do take your network to production. It is on an entirely different machine. You have absolutely no intention of doing any training on that machine.
Right.
You train a network on some very powerful hardware, right? It takes days and days to train. But when you take it to make prediction, you're running it inside some microservice, right? And that microservice is running on it has no graphic card most of the time. And lucky if it has some graphic computing ability. Sometimes it's running on smartphones and whatnot. And it's running on cheap devices. You want to minimize any kind of overhead, isn't it?
Yeah.
That's it. Go ahead, Supal.
No, so I was saying if you don't put network.eval, it will be just like one more epoch under the loop, network extensor. It will train one more time.
Exactly. It is effectively like a epoch. I mean, it is thinking of it like an epoch and wondering why you didn't call backward instead. Yeah? So that's what happens. All right, guys. So that is that. So you get predictions. Nissa, does that clarify your point now?
Yeah.
And now you plot it out. So you look at the plot, it's reasonably good. And you can do, sometimes you notice that there is a funny kink here, right? And if you actually use less number of epochs back to 2000, you'll realize that it doesn't have that level of complexity. It hasn't overfit the data. Do you notice that? The curve is simpler.
My experience.
Yes, it sort of goes to the heart of all of those topics. So now I'm going to show the code for mini batch. And this one, the gist of it is here, I'm not creating the data as a data matrix directly. I wanted to show you how to create a data set by hand. In the previous one, I did it. I created the X tensor and the Y tensor because I wanted you guys to get warmed up to it. Here I show you how you can do it. There is a class called simple numpy, which we'll deal with in the next few minutes. You give it, the way I've designed it is that you create numpy objects and you give it and it will make tensors out of it internally. You don't have to see it. Remember numpy, the PyTorch deals with tensors, but if you are hand generating data, you're likely to use numpy API to create a data. So this is what I'm doing. By the way, this was the function. 10 times 1 plus NP sine.
Sir, it looks always more beautiful if you know in the linspace 0 and 1 you put np dot negative pi and positive pi.
Yes.
That also creates a very beautiful data.
Yes. So you guys play around with all that. Huh? And then have you already played with that, Sukhpal? Play with that.
No, I did create some fake data sets.
So guys, remember what was the point of a data set? A data set is just something that will give you the feature tensor and the labels, target tensor. Now, what does the loader do? Remember, data loader's job is to slice it up into mini batches. Unfortunately, in the deep learning community, almost every library, it doesn't use the word mini batch size. They consider it too verbose. They feel that everybody understands it. So they use the word batch size. But batch size is actually, in a more theory part, it is the mini batch size. So I've taken a pretty big batch size, 32, right? Because I wanted it to learn quickly on my hardware. You can start with 1 and we'll see, or 2 or something like that. Do you notice this parameter shuffle is equal to true? What it does is every time you run through an epoch, it will reshuffle the data, right? Now there's a bit of, so now what I do, so this is the use of a data set in this. Let me quickly go through the code of that. The rest of the learning is simple with one change. Now, one step is not one whole epoch. So for a given epoch, you see another for loop inside, guys? So these are the mini batches of data. Data is a mini batch. Maybe I should have used the variable batch. Batch and label, data and label. You feed the data into the prediction engine network. It will produce the results, exactly the same code. And we start accumulating the epochs. Now, the number of steps will be much more, right? So you see it run. And you notice that the epochs are running slow. Are you seeing this, guys? Why are they running slow? Because each epoch has thousands of steps or hundreds of steps. So it will run its way through, and when it does, so the more steps you run something through, the better the learning. But at the same time, if your mini batch is too small, it screws up with the learning because it's too, it keeps fluctuating all the time. Are we together? Right. So you see that here. Look at this. When you look at this graph, do you see how much the loss fluctuates in mini batch? It does. In stochastic, it will fluctuate even more. Now you look at this curve, it sort of has fit the data perhaps a bit better than this one, the previous one.
Yes,
Would you say that, guys?
Yes, sir. A little smoother.
Yeah, it's smoother, but it has also begun to show some slight dangerous signs of overfitting too, a little bit. Mm-hmm. Right? So you have to then worry about the regularization aspect of it. So this is with many batches. Guys, is this code now simple and easy to understand? The only thing is that you go with, for every epoch, for every mini batch, you do exactly the same steps. What do? You make prediction, you compute the loss, you do back propagation of gradients, and then you learn from that. You take the step, gradient descent step. That's it. And that is the heart of learning as far as PyTorch is concerned. All of machine learning, it looks at essentially the predictive modeling part as just these 4 steps. So now you get the mini batch. Now, this is the answer. Now, last of all, we want to do the stochastic gradient descent. What is it? It will, one step is just one data instance, right? We can do it very easily. All we have to do is take the previous bit of code, but here I've set the batch size to 1. Nothing new. Batch size is equal to 1, guys. Huh? So now when I run through this code, what happens? It takes a very long time. You notice that this will take 6 minutes and 32 seconds, which we don't have, right? But what does it look like? Look, do you see the learning? The loss keeps fluctuating, right? It's a strange world. And then you get this curve, which is pretty good, but a bit of overfitting perhaps. So this is it, guys. And so this is it.
Sir,
Right?
one
Mm-hmm.
in mini batch size, how to decide the mini batch size?
It's a hyperparameter. You have to play around and do it.
Okay.
And so this brings up the whole world of hyperparameter optimization that I referred to before. Right? We'll learn about that someday.
Sorry, Asif, can you explain the inner loop in the mini batch?
Yeah, let me do that. So see, this is for the epoch, right? For each epoch. Now what this does is, this for loop is interesting. When you iterate over the data loader, it will give you, each time you go to the data loader, it is like, this is Python's way of saying, data loader, give me next. In Java, you say next, right, on an iterator.
Is it like bootstrapping, sir?
No, nothing to do with bootstrapping. See, imagine that you are sitting in a shop, right? Or remember that guy, the shovel guy, the sand and the shovel. There is a whole pile of data that the data loader is sitting upon. Who is the data loader? He is the guy with the shovel, isn't it?
Yes.
So when you iterate over the shovel guy, what will he do? For each effort that he puts in, he'll return you one shovel worth of sand. One shovel worth of sand is this little bit of data, and it's X, little bit of X, and the associated Y, the labels. Are we understanding this now?
Yes, sir. I understand that. Yeah.
So you can imagine that to go through an epoch of one pile of sand, you will go through many shovelfuls of sand, and that is it. So each shovelful, you're using it as a learning exercise, and so you do the same inner learning loop. This loop, Rafiq, you're familiar with by now, right? This is a familiar. So this is the way to think. See, guys, make it very real for yourself. Bring your own metaphors or your own, real world pictures. If in the beginning, when you're learning it, it really proves useful to think in terms of something like that. I think of it as sand and shovel guy. You think in terms of whatever makes sense to you. But remember that you need to make those mini batches somehow very real to yourself. That's all this for loop is.
Right. So the inner for loop, the data for each iteration corresponds to one batch, mini batch.
Yes, one batch. One mini batch, rather.
Yes. Yeah. So it's an N in our theoretical discussion.
Exactly. In the notes, it was a little n.
Yes, little small n. Yes, understood.
Excellent. You absolutely got it.
So do we really need to set the flag over there? Sir? Start true and false.
Oh, this is just for me. Otherwise, what happens is that it will print value in every single step. Do you notice that there's this little and start? I want to print this only once per epoch. I don't want to print the value every step.
Yeah, got it, sir.
That's that. So this is the stochastic gradient descent. Just set batch size to 1. Now, let me show you how the code is written, guys, because now we need to go. So guys, play with this, but let's start peeling the onion. I was hoping we'll do it today. It's already 10:13. Let me give you a quick overview, maybe on Saturday or next, I suppose, next Wednesday, we'll go deeper into the code. Where is the code? The code is, no, this is the notebook. So where do you find the code? It is not in the notebooks, it is in SVLearn. It is here actually in the approximator. Go there, regression network. So here, this code is something, actually there isn't enough time. All right, let's take next Wednesday by starting with walking through this code. See if you can read through this code. I have commented it forward, right? And we need to understand this. But let me at least do the init part. So init part is in constructor. People in object-oriented programming use the word constructor. Constructor means you sit and build an object. So when you build a network, here is where we build a network. So here it is. We're building one layer at a time. See, we are not connecting those layers at this moment. We're just building them one at a time. So what are we doing? The first layer has input dimension and number of hidden. And here I've hardwired things. Do you see the hidden layers? 128, 64, 16.
Yes.
So I have 3 layers. First layer with 128 nodes, second with 64 nodes, third with 16 nodes. Okay. And so I build this. There's nothing. This code, guys, does it look easy to understand? How many edges for how many things come in and how many things go out? That's it, input out for each linear layer. Anybody wants me to explain this particular line 36? And if you're lost with the Python code, guys, remember Saturday we'll do the remediation.
Creating the layers.
And so you notice that initially I used to assume ReLU, but I happened to just, while playing with this code, I made it 10H. If you make it ReLU back again on your laptops, I would suggest change it to ReLU. It will run much faster. And the forward pass, this is the one that makes the prediction. This code looks at this moment arcane to you, but I'll explain it to you guys later. Just glance through this code. We need to carefully walk through it next time. Now, guess what this pretty table does?
Formatting, sir.
Yeah, it just does a formatting, nothing magical about it. Right? And this is the simple NumPy data set. So if you have one dimensional input and one dimensional output, here is a little bit of code that makes it easy for you. Huh? I will this much and understand that, it will be good. Huh? Over the try to read through this code, see how much you understand. I don't expect you to understand because I expect you to understand the notebooks, guys. Huh? But this part of the code, I'll carefully explain line by line next time. This, by the way, is creating that helper method that created the regression data. As you can see, I used this function 10 sin x and I added Gaussian noise to it. This is the builder of the plots. Remember the two plots with two side by side? This builds the plot. So this is just Matplotlib. Again, I hid it because some of you are new to Matplotlib. So I hid that part. And by the way, one of the things I will do eventually this weekend is I'll get you to load this up in PyTorch so that you don't have to open a notebook. You can run this code and debug it in your, not PyTorch, sorry, PyCharm or PyDev, Eclipse, or one of these debuggers, or in Spider, and you can just debug it right there. Like find mistakes and so forth. So do you notice that I tend not to write long paragraphs of code in Jupyter notebooks?
Yes, sir.
That is the practice you should follow. Usually when you see a lot of junk code in Jupyter notebooks, it's a clear sign that the person is not doing very disciplined coding. All right. So, all right, guys, it's almost 10:17. I would like to reserve the next 10 minutes to, I said 10:30, to taking question and answer. I'll just summarize this week. What did we learn? We learned about neural networks property as a approximator. We learned about what activation function is, at least on a very conceptual level. It's some form of distorter. And then we learned about one more thing today, gradient descent, and three kinds of gradient descent. The batch gradient descent, which takes one big byte of the data. The whole data set is 1 byte. Then there's mini batch gradient descent, which takes small bytes of the data, shovelfuls of the data. And the third is the stochastic gradient descent, which learns from 1 grain of sand at a time. Right? So if you think of a pile of sand, a batch means you take the entire heap of sand and you sort of somehow spill it all over your project. The mini batch gradient descent is you take it shovelful by shovelful and you use it. And stochastic gradient descent is you literally build your project and your paving stones and whatever it is that you're doing, 1 grain of sand at a time. That's sort of a very, I don't know, metaphor, analogy that you can carry. That's that. Right? And so the PyTorch and every machine learning framework in this space, but PyTorch in particular, it explicitly asks you to do 4 explicit steps. Given a network, it asks you to make a prediction. Well, you say, how can it make a prediction when it's all wrong? We haven't trained it. It says, no problem, just start randomly and make a prediction. Then look at the mistakes from the prediction, the loss, then compute the gradients because you lead the gradients with the gradient descent step and then do the gradient descent step. And then repeat, keep repeating. till you're satisfied with the answer, till the network makes good predictions. In other words, till your loss has decreased to a level that is acceptable to you, right? Or at least it has stopped improving. And that is using PyTorch for machine learning, guys, for AI. So all of this API is new to you. Trust me that once you get familiar with it, it will look very natural. But the first time you encounter it, all of this, it looks a bit intimidating, which is why we are going slow, and which is why I am giving all of this, help, making it simpler for you. But so at this moment, I would suggest for this week, the code at this moment will look hard. Definitely make sure you understand the linear regression code here, right? This notebook. Review every single line of it, understand it. If you don't understand, ask questions from us. I'm there, the TAs are there, other participants are there who will help you. Definitely don't hesitate in asking questions. Make sure that this part is crystal clear. Next Wednesday, we'll deconstruct and unpack that simple neural network that we created. Right? And if you get that pattern, then everything else, everything you will learn in this workshop all the way till January follows exactly this pattern, exactly this pattern. So you're laying down a pattern for the first time. It's long and strange. Once you get familiar with it, this is the pattern we'll always follow. That is it, guys. So I'm stopping the recording so you guys can ask questions.
Asif, the three methods that we learned today, do we have any reasons?
Hang in, guys. 1 second, please.